Hello, everyone. Good to see you today. Welcome to the second workshop on foundation models. In order to promote the development of foundation models, Baidu, in collaborate with MB ZUAI, the Chinese Academic Science of China, Zhejiang University, and Hong Kong University jointly hosted the workshop. Previously, we know that the main reason why the vision foundation models cannot cover hundreds of tasks is because due to the conflict between the tasks. Therefore, we need to first solve the problem of conflict between the, say, like the hundreds of tasks. We need to take into account the performance. When we finish training the foundation models, we need to deploy it on the multiple devices. Therefore, we need to into account both the performance and the efficiency. In terms of the technical solutions, we have the human brains. We know that the human brains has different regions that it can take over, like the video information and the sound and so on. So we have built the you can like the MOE based the search space to solving the problems. And by doing so, we have once developed the largest foundation model, the computer vision foundation models in the industries, which have the 17 billion parameters and covering more than 20 tasks, basically such as visual human bodies and vehicles, and also it can be deployed very efficient. When training the foundation models, we have using some we can train the foundation models using the multiple hundreds and thousands of the GPUs together. And also, we have deployed this in the Baidu's product. You know that Baidu's ACE intelligent transportation engine is a full stack intelligent released by the Baidu the Apple, which integrates the vehicle road travel through space. This solution supports multiple subcategories, including the intelligence, high-speed transportation, intelligent traffic management, and intelligent transportation, and also vehicle road cooperation and autonomous driving. The current transportation project has been implemented in over 100 or more than 100 cities in China. We have deployed these technologies through all the countries, all the cities in China. And also, we can quickly build the capabilities and the continuous close problems. However, you know that this approach has issues such as the low iterations, like the adaptabilities to scenarios and difficulties in establishing the barriers in traffic. So, like I said, using the computer vision foundation models, we can doing the end-to-end solution for all the scenarios, and we also have released the earning traffic to the public, and you can check it in our website and try to both the computer vision, the Beamer and the earning traffic, we have released to public as a free version. You can using it by free. And I mean, recently we have moved to the computer vision foundation models to the multimodality foundation models. As you can see, there are hundreds of the multimodality foundation models during the, I think maybe just during 1 year, we have there are lots of models here. So for the multimodality foundation models, you mean the image and the text are essentially two different ways to present. For example, we can present the geometrical information. Also, we can use the text and vision to represent the same meanings. This is because the different expressions can be present different aspects. We also analyze this, what introducing a new modality means for the perspective of language model. I think most the multimodality foundation models is they bring the pre-train of the language models and using the adapter to like to learn the visions presentations into the language. At the output end, text serves as the final format. For example, we can doing the QA like the query to like the model to answer everything we want, like the GPT-4 vision and the GPT-4o, right? So here is today's schedule, and let's welcome someone to do the opening remark. Okay?
Thank you. Hello, everyone. Thanks for thank you for nice introduction to foundation models. So let me introduce our agenda for today. We'll have a keynote talk from our guest speaker, Ani, and then there will be a poster session break. So the poster sessions will happen in the morning and the evening time, and it will happen in the exhibition ARC building, exhibition center in ARC building. We will be having 3 oral presentations from the accepted papers in the afternoon as well. So today we have a list of exciting invited speakers. One of them won't be unfortunately able to join due to the visa issues. So we'll be having these talks over the period of today. And in this workshop, we have got 11 accepted papers. 2 of them are going to be in the archival proceedings. 9 of them will be appearing as short papers. Hello, can you? Okay, so maybe I can try speaking up a bit. So for those of you who are joining online, so this is the link to join. And with this, I would like to move on to introduce our first speaker for today. So Ani is the Senior Director of Computer Vision at the Allen Institute of Artificial Intelligence here in Seattle. He's also an affiliate associate professor at the Computer Science and Engineering Department at the University of Washington. Obtained his PhD from University of Maryland, College Park. He spent 5 years in Microsoft afterwards. So he has been awarded the Best Paper Award in CVPR 23 last year, and an Outstanding Paper Award at NeurISP 2022, and AI2 Test of Time Award in 2020, and an NVIDIA Pioneer Award in 2018. So with this, I would like to give the floor to Ani. Thank you. You can just show.
Okay, yes. Okay, good morning, everyone. Great to start off the workshop, early in the morning. Okay, so today I'm going to talk about building foundation models for vision, language, and robotics. So large language models are omnipresent. If you walk around CVPR at the workshops or conferences, you'll see that my screen is not sharing. I think we can. Or maybe you can. You want to plug in? Okay. Thankfully, only one sentence in, so I'll start again. So large language models are omnipresent. They're powering so much of our work and research here at CVPR, but they're also making their way into our products. And these foundation models for language are really trained on trillions of language tokens. But these tokens tend to be homogeneous in modality. All of the input tokens are language, and all of the output tokens are language. There's an abundance of tokens in this form on the internet. And interestingly, a lot of the data that's used in pre-training is at least somewhat aligned with the downstream tasks. In the multimodal world, things are a bit different. By definition, a lot of the work that we're interested in consists of heterogeneous inputs and outputs. Some of the domains and some of the problems in the multimodal world also are in the data scarce regime. And then, of course, we're also interested in training multimodal models for extremely niche applications. And so in today's talk, I'm going to talk about building these large-scale multimodal foundation models in each of these three challenging situations. And I'm going to start with heterogeneous data. Unification has been extremely hard in computer vision, and that's because our data tends to be heterogeneous. If you take a single image, for example, there's so many different kinds of structured outputs that you want to extract. You want to write a caption, which is language. You want to detect objects, which are bounding boxes. You want a key point estimation, which are points, and so on. And then sometimes you want to go from these structured representations back into pixel space. And I haven't even started talking about 3D, video, audio, and so on. And partly because of these challenges, a lot of the best work coming out even today tends to focus on single task, highly specialized models. And that continues to be the trend at CVPR. A few years ago, when BERT came out in the language space, there was a push towards unification in the vision and language space. And you heard about models like VilBERT and VisualBERT and so on. And the difference here was that there was a push towards large-scale pre-training online for a shared backbone of parameters. And then people introduced task-specific or even dataset-specific heads in order to get this model to multitask. Then there was another push a few years ago, a couple of years after the VilBERT and VisualBERT pushes, where there was unification within a modality. So if you were producing language, you shared parameters. If you were reading images, you shared parameters. If you were producing bounding boxes, you shared parameters. The next step towards unification has been unified I/O. And I consider this the first big, large-scale, homogeneous model. Unified I/O, from a top-down view, really looks like a language model. It accepts an input sequence of tokens, and it produces an output sequence of tokens. At the input, these tokens can not just be language, but they can be images, they can be masks, they can be segments, they can be bounding boxes, and so on. And the same goes for the outputs. You can not just produce language, you can produce visual outputs, you can produce continuous outputs, and more. And as a result, unified I/O is a large model, but with a single set of parameters, it can perform many, many downstream tasks in computer vision and natural language. So how do we get this unification? At the core of unified I/O is a transformer encoder decoder, right? And so it can accept images, it can accept language, and of course it can produce language. This is fairly straightforward, so I won't go into the details here. The interesting part comes when you have a task like, can you segment an object for me? The output modality of segmentation is a binary mask. Here we leverage a very rich body of literature in image serialization and deserialization. Essentially, we take a model like a vector quantized VAE, and we convert the target image to a discrete fixed dimension embedding. And now, instead of producing pixels, instead of having a loss function on pixels, we get the model to produce this quantized representation. Once the model produces this quantized representation, you simply pass the output tokens into a VQ-VAE decoder in order to obtain the segmentation. So this is a trick to bring in modalities that are not naturally serial into the unified I/O framework. And so any data that can be serialized and deserialized in this way is now fair game to unified I/O. So this was work that we had about 1.5 years ago. And since then, we've expanded unified I/O to unified I/O 2.0. And so now we're not just able to accept images, but you can accept images, videos, audio, text, and you can produce audio, you can produce language, you can produce any representation that can be represented in pixel space, and you can also produce actions that can be used to control a robot. So when you talk about these extremely large models with so many kinds of modalities at inputs and outputs, as you can imagine, pre-training is an extremely important piece of the puzzle. So at pre-training, we leverage data on the internet. That's in the form of text, that's in the form of audio, that's in the form of images. And of course, images naturally extends to video. But importantly, it's crucial to get multimodal information from the web. And so, for example, if you scrape a YouTube video, you can get images, you can get audio, you can get this model, get these images captioned by a captioner. And so now you have a description of the video. And so you can get text involved and so on. And so we train on extreme large amounts of data from the internet. There's many different loss functions that we use, and I refer you to the paper for that. But in essence, when you have multimodal data, one way to pre-train your model is through a mixture of denoisers. So here's an example. Imagine you have this YouTube video, and so now you have images, you have audio and text. You choose one of these modalities as your target modality, and you remove it from your input modality. And so you say, if I have n-1 modalities at input, how do I predict the nth modality? Then another way to do it is to not completely remove a target modality, but to add noise to it, to corrupt it by masking some critical parts. And so this becomes a denoising task for a single modality, and it encourages the model to build joint embedding spaces across modalities. So the example that you have in the middle is exactly the example I spoke about. But as you do this, you can start teaching your model, different things about the physical world that are important for your downstream tasks. So for example, if you take stereo images, or if you take images that are captured from completely different locations for the same part of the physical world, you can mask one image and get the model to reconstruct it, which would require the model to parse the unmasked image and infer that, okay, what was there is the white cushion, for example. Another thing you can do is you can take videos of a robot moving around or people walking around, and you can ask the model to predict the next observation conditioned on your previous observations and conditioned on the robot action. So these kinds of pre-training strategies were extremely helpful in making the model capable at downstream tasks. Now, training large language models, is a bit of a science and a bit of an art. There's so many tricks as you get into the spaces of 7 billion parameters, 70 billion parameters, etc. Adding multimodal data can make this task very, very challenging. And so we've noticed that if you start with the text-only modality, you can get your loss curves, you can get your gradient norms to behave reasonably well. You add a second modality, things get fragile. You add a third modality, things get extremely fragile. And so, we've come up with a very stable training recipe that can be used when you start adding many, many modalities. So, recently there has been more interest in creating unified models. For example, GPT-4o. And I would encourage people to go to our code base. Our code base is completely open. All our training code is available. All our test code is available. All our training recipes are available. If you want to start building models like GPT-4o, and you want to learn the tricks of these training recipes, they're all available here. All of our work is completely open source. So I'm not going to go into each of these nitty-gritty details about these piece of art and science of building large multimodal models, but happy to answer questions offline. Okay, once you pre-train this model, once you finally got this model behaving well at pre-training, how do you instruction fine-tune it, right? So there's three kinds of data that we use. One is many of you have produced very, very fine instruction tuning data sets for multimodal data. So of course we throw that in. Then we can take single task data, for example, segmentation, and write custom prompts. But another thing that we can do to go from a set of tasks to a spectrum of tasks is really to combine different data sets into more complex tasks. So for example, if you had in the bottom right, instead of saying detect all the objects or detect all the animals, you can say detect the carnivores, right? And so this requires you to not just do animal detection, it requires you to use some information from your language space to understand that the cheetah is a carnivore and maybe the bison or the deer there is not a carnivore. Similarly, you can take key point data sets and referring expression data sets, and you can say, can you detect the shoulders of the person playing defense in this image, right? And so now you can start getting lots of interesting data that can force your model to read the instruction well. I'm not going to go through this pie chart, but safe to say that, my colleagues who did all the heavy lifting on this, had many, many, many weeks of, sleepless nights getting this together. Okay, so we've trained Unified AI 2.0, and we test Unified AI 2.0 on many different benchmarks in vision, language, video, audio, etc. I'm not going to go through these numbers, but I thought in the spirit of this talk, I'll show you, the breadth of tasks it's capable of via qualitative examples. So, whenever we build any sort of multimodal models, the litmus test is, can it caption? If it can't caption, it's hopeless. So here's the basic litmus test to say, well, write a short caption, write a long caption, answer some basic questions about the image. This is easy, and I won't read out these answers here. But then you can ask the model to do image editing, right? Remember, this is a single set of parameters that are performing all of these tasks. You can say, make the image haunted, convert the colors of some objects, change the style. Then you can say, generate music about this scene. So this generates music for the scene above. And then you can ask it to generate music about the... Right, so you can see that it is respecting the pixels to some extent to at least realize what the style of music might be for this particular image. Then, of course, you can do object detection, you can do segmentation, surface normals, and more, right? Now you can also do things that typically we've become accustomed to with language models, but we don't really do these tasks in vision. So you can say, here's an image, and I want to build a computer vision system. And so this requires me to not just detect objects, but also output them in a particular format. And so here I've asked the model to recognize all of the fruits, and then tell me what colors they have, and then output it in a JSON format. The bottom example is quite interesting. I want the model to recognize the brand of the car on the left, the color of the car on the right, and then use that to do image generation for another image. So as you can see here, adding instruction tuning data sets with a spectrum of tasks has allowed us to sort of zero-shot test the model with lots of interesting tasks. Then the model can read out text.
Many animals of even complex structure, which live parasitically within others, are wholly devoid of an alimentary cavity.
Right. So as you can see here, the words in this text were not very easy words, but the model does reasonably well. You can do, because the model is 3D aware, because of the data I showed you, it can rotate images, right? And then, of course, it can do video understanding. So you give it a video and you ask it a simple question, and it can answer it. We've also tested the model on robotics tasks. All of this is done in simulation. The model is too heavy to deploy onto a real robot in real time. But in simulation, you can give it a task and ask it to predict actions. And then you can take these actions and put them into a simulator to see if the model is doing reasonably well. So here there's a compositional task that requires this robot to put something in something else, and it does it. And here's a task which is navigating around the environment. Okay, hopefully I've convinced you that it is possible to build large foundation models when you are dealing with heterogeneous data. And the other thing that I was clear in these slides is we use lots and lots of data. But what about data regimes where there's very little data available? How do you build large foundation models in this domain? One such domain is robotics. Getting real-world data for robots is a nightmare. So this is a famous paper from Google that came out maybe about 24 months ago called the Robotics Transformer 1. And it's very interesting to read the text in this paper. They said, well, they collected 100,000 episodes for a single task, right? This was a task of going and picking up something or opening a drawer and picking up something. And these 100,000 episodes took them 17 months to collect with 13 robots. So as you can see, it's extremely slow to scale up data, and it's going to be extremely expensive. And so the way to get over this boundary, the way to move robotics into the large data regime is really through simulation. And so here's a teaser to what I'm going to show you over the next few minutes. So this is a new model that we have that we're presenting at CVPR this year. It's called Spock. So this model is trained only in simulation, but it's trained with a lot more data than has previously been trained. There is no real-world adaptation. The model only uses RGB. There is no depth. There is no LiDAR. There are no expensive sensors. It's a very clean architecture. It's not modular. There's no mapping. It's trained with imitation learning. Importantly, there is no human data involved. And in spite of these, you can call them challenges or opportunities, right? We've created a model that can be proficient at long horizon tasks in navigation and manipulation, not just in sim, but also in the real world. So here's a teaser for what this model can do. This is an apartment. The model has never been in the real world. The model has never seen this apartment in sim or real. And it's trained end to end. It makes no assumptions about where the objects are located. And it goes around, it explores the environment, it tries to pick up the object, it fails, it recovers, and then it picks it up. And the key to this is really scale. We've scaled the environments, we've scaled data, and we've scaled the way we train these models. So 2 NURIPs ago, we took a big step towards scaling simulation. Simulation in the past dealt with 10, 20, 30, maybe 100 scenes. Each of these scenes was meticulously created by some graphic designer or game artist. And so we took a step towards scaling up simulation by our system called ProcThor. So in ProcThor, which stands for Procedurally Generated Environments, you start with a specification. So you can say, I want a 1-bedroom, 1-bath apartment, and this is how apartments should be connected to each other. And then you use a heuristic approach, a heuristic set of procedures in order to generate a scene. So at each step of these iterations, you can sample a floor plan, then you can sample objects, you can sample lighting, you can sample materials, and then you get a rich environment that can be used to train agents. And what this gives you is this kind of diversity. And we showed in that work that as you add to the number of houses in simulation, your success at robotics downstream tasks goes up. So how can we build upon this? How can we expand upon this in order to give the user more flexibility? So instead of writing, this little ugly tree structure, how can we give them more flexibility in defining what kinds of environments they want to train the robot in? And second, how can we extend this approach to more domains? We don't want to just stick to houses. You want this to work in your Amazon factories. You want this to work in healthcare situations. And every time you don't want to manually write procedures. And so towards this, we have our new work called Holodeck. So Holodeck is a framework to use large language models to be able to input rich descriptions of the environment that you want to produce a 3D environment. So gone are the days when we have this, ugly little tree structure. Now you can simply say, I want an arcade room with a pool table in the middle. And what Holodeck will do for you is use a large language model to first determine the layout of the scene. Second, determine the positions of the objects, determine the lighting, determine determine all kinds of details about the scene to produce something like this. So this is 3 professors' offices connected to a long hallway. The professor in office 1 is a fan of Star Wars. And you see here, they have 3 offices. You can go in, and Holodeck will even place certain objects based on its repository. And this gives you a lot of flexibility. You can customize anything in the environment through natural language. You can say in the top left, this is an apartment for a person who needs to use a wheelchair. And what Holodeck does is it chooses doors and designs doors and windows that are large. The right one might as well be, I live in Seattle. And so it's going to have large windows to maximize the amount of light that comes in. I don't know why it's going ahead. You can also customize objects. You can customize materials. So I'm going to skip over exactly how we use a large language model here, and happy to talk offline. I'm just skipping in because of time. Okay. We also introduced a large repository of objects that has now become the de facto repository to train 3D foundation models. I won't talk about 3D work here, but these kinds of large repositories can convert sterile environments like this. No one's house looks like this, right? Everyone's house probably looks like this. And so how do you convert simulation to really look like real world environments where you want your robots to? Okay, so now we've created simulation environments at scale. We have simulation environments that are diverse, that are rich, that are flexible to create. So what does simulation give you? Simulation, the key thing that simulation gives you is access to privileged information apart from scale, right? So when you have a simulated environment, you know exactly where the objects are, you know what categories they are, you know what their masses are, you know what their volumes are, and so on. This is all information that you don't know in the real world unless you annotate. And so given all of this information, you can now write privileged planners, which can serve as training data. So remember, you do not want to rely on this information at test time, but it's perfectly fine to use privileged information at training time. And so we can write planners for navigation, planners for manipulation. You can also do all kinds of scene-aware planners. For example, go to the most accessible container so that it's on the ground plane. Because you know exactly where objects are located, planners work really well. So for example, here's an example of a training video, right? So you say, pick up a pillow, and now you have a training video of a robot picking up a pillow. You have all the actions at every time step. You have all the observations. And this allows you to do imitation learning on a model. So we use roughly 1 million trajectories obtained from 100,000 houses in order to train Spock. Spock stands for shortest path Oracle agent, right? And the reason it's called shortest path is planners will give you the most efficient way of executing an instruction. And then when you train on this data, you can now deploy this model in the real world without access to any privilege. So at each time step, our model gets a language goal description. It gets 2 camera frames. They're in RGB. One is a camera that allows the agent to see where it's going. And because we're using the stretch robot, it's a kind of a strange configuration where the arm goes out to the right. And so you also need a little camera for the arm to be able to see what it's picking up. And then using a transformer encoder, you get a goal-conditioned visual representation. And this goal-conditioned visual representation is produced at each time step. So you can take the representation at each time step. You can take all your previous features. You can, of course, have some sort of temporal positional embedding. Then you can give this to a transformer decoder, which can produce the actions that the robot must take. So here is something that we found very interesting. So this was a very controlled experiment where we were training the model for the task of object goal navigation. What is this task? You are in a completely unseen environment, and I'm asking you to, for example, go find my keys. So you must explore this environment, and you should navigate until you reach right next to a set of keys. So at training, we use a planner. So what you're seeing on the left is an example of a training video, which is trained on shortest paths. And in spite of being trained only on shortest paths, what we observe at test time in an unseen environment is that the robot is able to explore rooms, backtrack, and exhibit many kinds of behaviors that are required as you explore an environment and find objects. And this has been extremely interesting to see, and we've noticed this at scale. Right? So when we take all of the training data that we have, we can start training the model on a variety of tasks. So for example, you can say navigate to the kitchen and find the fruit which is highest up, right? This might seem like an artificial task, but these are the kinds of tasks that you might want your robot to be proficient at. And so this works well in simulation. Then, of course, we take this model and deploy it on the real world, and you'll see a few videos. So this is an apartment that we have constructed next to the AI2 office. And so a lot of our test happens in this apartment. This is completely unseen at training time. And so you can see that the model goes around, it fetches an apple, it does object goal navigation by going around and finding a toilet. And we find that when we train with imitation learning, the model is very proficient at exploration, navigation, and pickup. So what matters? How do we get this model working? So we find that scale matters a lot. And as you start scaling up simulation, your numbers go up from like the low teens all the way to about 60%. But crucially, scale is not the only thing that matters. It's the diversity of procedurally created training environments that is key. So at the same scale, if you train on fewer houses, you get lower success rates. But as you start increasing the diversity, generalization improves. And this is not a very surprising finding. We've seen this in language, we've seen this in vision. And it's good that we're seeing this in robotics. But of course, the key has been, how do you get the scale and diversity? And that's what we've been able to show in simulation. Okay, so now we've trained this model with imitation learning. But of course, imitation learning continues to suffer from insufficient state space exploration. You're training a model with a planner. Planners tend to work most of the time. And so the model knows, well, if I'm going along this path in the middle of the room, then I'm able to like predict my next actions and perform the task. But what if the robot takes a wrong turn? What if the robot goes close to a wall? Imitation learning doesn't actually teach you how to recover from these sorts of mistakes. Of course, you can start writing rules and you can start adapting your planners to, give it all sorts of situations, but there's always a long tail of situations that you can't code up in your planners. On the other hand, reinforcement learning teaches agents through trial and error. In reinforcement learning, what we typically do is we just place the agent into an environment, we give the agent an action space, and we ask the agent to sort of play around with the world. And whenever it performs a task, we give it a positive reward. So you would think that reinforcement learning is the answer. But of course, we've been using reinforcement learning to train agents for these kinds of tasks. And things haven't really worked out really well there either. And the key has been that reinforcement learning in the past hasn't moved to, I would call it, modern architectures. We're still using a CNN to encode images. We're still using a GRU to add history. And the reason isn't that we've been lazy. The reason is that when you go to large transformer architectures with lots of data, with lots of parameters, training has been unstable and training has been slow. So this is our latest work that we've just finished a couple of weeks ago called Polyform. It has a very similar architecture to Spock. It has a transformer encoder to encode your observations, and then a transformer decoder to predict your actions. But Polyformer, in spite of having a large number of parameters, is trained with reinforcement learning. And that's why the small difference in this architecture is that instead of just having, instead of just outputting action, it has not just an actor head, but also a critic head, and it's trained with PPO. The key to training this, the key insights in this training recipe are to hugely increase the number of parallel rollouts. And we also have a particular batch size recipe that works, that makes training a lot more stable. And so, I'll refer you to the archive paper on our website to get the details here. What you see here is really interesting. So on the y-axis is success rate at this task. On the x-axis is the number of training steps. Mind you, this is log scale on the x-axis. So just about 18 months ago, we were on the lower arrow. So the best reinforcement learning agents on this benchmark, and if you look at many other papers out there, you were seeing pretty low numbers, right? Then we hugely scaled up simulation, and we said, let's go the imitation learning route. And then we saw a healthy, almost 20-point improvement when we went from previous approaches to Spock, which I just presented. What reinforcement learning allows you to do is completely break this barrier. And really at this point, it is my belief that we are compute limited. So if you have any free compute, you send it our way. And I'm fairly confident that with a little bit of tuning of our training recipe, we can probably get object goal navigation well into the upper 90s. So this is actually very, very heartening to see that scale has helped not just one learning paradigm, but another learning paradigm as well. So here are videos of now not Spock, but Polyformer doing long horizon tasks. So now we can say, don't just find one object, go find a sofa, go find a toilet, house, plant, and book. It goes around, it looks at objects, it issues a found action, and then it says, okay, so I still have to find the toilet. It goes there. And then you can, you can add a vision and language model on top of Polyformer and get it to do an even more complex task. You can say, can you find a book titled Humans? And so it sees the deep learning book there. It says, I don't think that's the book titled Humans. It goes around, it explores, and then you'll see that at some point it finds a book called titled Humans, and then it says done. Okay, I have a few minutes left. Actually, I have quite a bit of time, but yeah, I'm going ahead of schedule. And I'm going to end with a couple of slides on a third domain that we are very interested in at AI2. And so here I'm going to talk about building planet scale foundation models for remote sensing. So remote sensing is actually an extremely interesting domain. We have several satellite clusters that go around the Earth, capturing images of the Earth at different resolutions. And many of these satellites are paid, but some of the satellites are completely free. So for example, the European Space Agency has some satellite clusters that produce RGB images and some other spectral bands of the entire Earth every 2 weeks. And so what we're interested in is to use freely available satellite imagery at a planet scale and use modern computer vision techniques in order to monitor the planet for lots of different applications, whether it is renewable energy resource deployment, whether it is deforestation, urban growth, freshwater resources, oil rigs, etc. Okay, so in order to train models for this application, you of course need a lot of data. But the data available for remote sensing is a very different kind of data. You can't just use image text pairs online and get powerful models. A, because there isn't a lot of text written about satellite images. And B, the kinds of applications that you're interested in satellite images are not very well aligned to simply producing a language caption, for example. And so we released this year a data set called SATLIS Pretrained. This is one of the largest data sets that are openly available. It has, hundreds of millions of labels. It covers most of the Earth. It has multiple satellites, which are all free, and all of you can download it and use it. And importantly, it has all kinds of interesting label information. And these labels are, in a sense, belonging to different modalities. So you can see point labels, polygon labels, segmentation labels, regression labels, etc. We're once again back into the land of hugely heterogeneous data, right? And so we haven't yet got SATLIS working on unified I/O. It is, it's quite challenging to get these models working in a very stable manner. And so you can say we're about a half a generation behind full homogeneous foundation models for remote sensing. What we've done here is design a model that can input multiple images. These multiple images can either be images over time, they can also be images from multiple satellites, and then have multiple heads based on the modality that you're trying to predict. And what this gives us is a foundation model that can be useful for lots of different downstream tasks. You can do all kinds of recognition at a planet scale, but the representations that you learn from this kind of foundation model are also useful for things like super resolution. And we found that we're now able to train very, very powerful models for super resolution, where you can input an image from a satellite cluster called Sentinel-2. This goes around the world every 2 weeks and gets an image like the one on the left. And you can produce from a model this high resolution image, one on the right. And so our goal here, our vision here for this foundation model is really to output all of the predictions of this foundation model on a weekly basis, which we've already started doing at this website called Satlas. And not only did we produce predictions on a weekly basis, we've also gone and backfilled for the last 10 years. And the idea here is to allow scientists in different fields to use the outputs of computer vision models to study the planet and make inferences about our planet, about the change that's happening on our planet, about infrastructure that is being developed, and so on. And with that, I will end. And so in summary, I spoke about 3 challenges in building foundation models. One is having hugely heterogeneous data. And towards that, we built the unified IO family of models. Second is working in data regimes where data is extremely scarce. And so here, I believe the key to overcoming this barrier of poor data is simulation. And this is our work Spock. And then a niche application, which is monitoring our planet for change. And this is Satlas. And with that, I will thank you all.
So if you have any questions for the speaker, yes.
Thank you for the good presentation. Just a question about the robotics application.
Yes.
So it seems that you only have one type of robot. Can you create an environment or simulate with different type of robots with different degrees of freedom, drones, humanoid, ground robot?
Yeah. So, I wrongly predicted that I was completely overscheduled, so I deleted a few videos. But we are we have actually tested this model on 2 robots. So we haven't yet built a model that is embodiment agnostic, which means you have to go into the simulator and you can simply pick a different robot and train the model again. So we've tested on Stretch and we've tested on Locobot. It's a smaller robot that has much lighter payloads, and it works just as well. We don't have any humanoid robots with us, but would love donations.
So you said you trained this Spock robot using simulated data.
Yes.
Can you consider that as synthetic data, for example?
Yes.
Did you have to do anything specific for the robot to be able to have similar behavior in your work?
Yeah, great question. So if you train all of the parameters in simulation, this tends to not work very well in the real world. The key is to use a visual encoder that is already trained in the real world. So for example, when I spoke about using CLIP or using SIGLIP or using Dino, those are models that are trained in the real world. If you want to improve numbers in simulation, you should unfreeze your visual encoder. Then the numbers in simulation really get close to 100. But the model does not work in the real world. If you want your model to work in the real world, the key is to freeze your visual encoder. The other thing that we found was, simulators are getting more and more visually realistic, but there is a trade-off between visual realism and speed of simulation. And if you want to train models fairly efficiently, I'm just saying fairly because it still takes a couple of days, it's important to reduce visual realism. In that case, we do extreme levels of data augmentation, far beyond what is used to train, for example, models in ImageNet.
We have a question over there.
I've been using Holodeck for my reviews. And I just wanted to know that right now, with Holodeck, when you try to create really complicated stuff, it's not as well as when you're trying to create really simple.
Yes.
So I just wanted to know your thoughts as to are there any next steps that you guys are working on that, or any insight on how we can address this stuff? Yeah.
So that's a great question. So when you go to complex layouts, particularly very large spatial layouts, so for example, if I want to say, can you design a full school for me? We find that large language models, A, tend to produce things that are not physically accurate, and B, they tend to, for example, not have symmetry. They sort of lose structure. So they'll generate a couple of rooms, and then they'll generate a corridor, and then they'll generate a room that an architect would not have put there given the context, right? So there's two ways to overcome this. One way is to say, well, when we did this work, this was an older version of GPT, and so you just wash your hands off the problem and say, I'll just wait for the next version to come out. But without going to that sort of extreme case, I think the way to do it is to see if you can add constraints to your procedure right now. So we found that language models will place furniture, will tell you which coordinates to place furniture at. But then some of these furniture pieces start colliding with each other. And so when we switch on physics in the Unity simulator, these furniture pieces just go away from each other. And so what we had to do was, convert the procedural layout to say, don't tell me where to place the furniture, but instead give me relationships between furniture. So tell me that the coffee table is in front of the couch instead of telling me the coordinates. And then using constraint optimization to then figure out the layout. We don't do this at a level of generating the layout or the plan of the house, but these are ideas that I would use in order to sort of bring in human intuition and ideas from architecture in order to produce these layouts at the same time while accounting for the frailties of language models.
Yes.
Yes.
You think you are halfway success with unified encoder for all the technical that is in this remote sensing. So what you think is the next to what is reasonable is also about scale?
Well, the reason is not really a technical reason. I think training a model like Unified IO requires extreme compute. And so we've been able to train at the Allen Institute, we've been able to train this using Google's TPU resources. And so we've trained 7 billion models. The amount of data that you have when you go to satellite imagery, because we're using historical data. So every image of every location on the Earth, every 2 weeks, backfilled for the last 10 years, requires a very, very long training time. And what we've realized is if we go from 7B to 32B, we can start getting this model training really well. So it's really a matter of a little bit of time and a little bit of compute. But I don't think there are very large technical challenges. There's, of course, the data is a bit different modality. And so the training recipes are still not probably generalizable. We're still in the early days of truly unified multimodal models. But I think that can all be figured out.
Yes.
Yeah, thank you so much for the awesome talk. It's exciting to see the scaling patterns in different fields. And I basically have two questions. One is that seems like the scaling pattern has been quite swift right now, and do we have like kind of expected timeline, like when's the time we might have like really big milestones that we are like using foundation models to kind of unify different tasks we are like working on right now and make it really a unified task and unified model that is really foundation. Yeah, this is like first question. And second question is like while we are seeing some like scaling patterns right now, we also find there are like models that cannot be easily scaled with scale, like vision models, like when we're scaling up MAE, the functionality is like really not performing better with more data on better like larger photo scales. So this kind of like potential bottlenecks that when we are facing the scale. So yeah, this after.
So I'm not going to take the bait and give you a date when this is going to happen. This just feels like a, teeing me up for an embarrassing moment. But I will say that I think, getting into truly homogeneous models, right, where every modality is input and every modality is output, is probably going to be one of the next waves in the multimodal world, right? And so you've seen GPT-4o. There was some recent work, I think it's called, I forget what the name is, from Facebook that came out a month ago. And so this is certainly something that a lot of people are going to try. I think, even though, I'm in the business of creating homogeneous models and extreme level unified models, I think there's still a scientific question that is unanswered, which is there true transfer from one modality to the other? What I mean is, yes, you can perform tasks that require multiple modalities. I'm sure the embedding spaces are getting closer and closer, but I don't think we have seen evidence yet, much to my dissatisfaction, that if we input more and more vision data, we can start getting better at language tasks, as an example, right? Or it's because of this audio data that depth estimation is improving, because somewhere the model is able to come up with more unified structured representations. I think that would be a really, really interesting thing to see. And I think that would be a trigger for everyone getting onto this bandwagon. Right now, it's a proof of concept that this is possible. But what exactly is the true advantage of this is, I think these are scientific problems we're still working on.
Any other questions? So maybe, Nia, I can go ahead with, first of all, thank you for a nice talk. So I had a question about unified I/O. I believe, as you mentioned, the heavy loading is kind of, heavy weightlifting is done by the autoregressive model. So did you see any limitation in terms of dense prediction tasks, like segmentation, object detection, depth prediction, where maybe this is not the optimal approach?
No, actually, the limitation really is in the quality of the VQBAE. So in Unified I/O 1.0, we used off-the-shelf VQBAE, and we found that even if you know the target, so if you cheat and say, I know the true depth, and I just sort of encode it with the VQBAE, decode it, and use that as my predicted depth, even then we found that our numbers are gated. And so in Unified I/O 2, we said, VQVAs that are trained on ImageNet aren't good enough for these kinds of modalities like binary masks. And so we had to train our own serialization networks, and that led to an improvement in tasks. In terms of what are the sort of limitations of autoregressive, one thing is speed, right? Like you want to, tomorrow, someone's going to take a unified I/O model and generate video with it. That is very, very slow. And so I think that is one of the big challenges of autoregressive models.
Thank you. So if we don't have any further questions, let's thank the speaker again.
Thank you.
Do have models that work rather well by now. They can track, detect, and segment objects across frames, even if those objects are moved around. And I show more of this video later. If we move those objects out of the frame, hide them under the tower, models are rather well behaved these days. However, I would also argue that quite a few challenges still remain to help particularly people in the sciences domain to really get these models to use. For instance, how do we segment objects in videos without collecting actually video annotations, right? I have some collaborators on the agriculture side, and they want to annotate pigs, chickens, or guinea pigs. They want to track those. And the classic approach would be to actually annotate those. And that takes a lot of time, as you'll hear later in this talk. Now, what I'm trying to tell you about in this work is how we can actually do that without ever annotating any video data at all. And I think the main message that I want to convey here is that foundation models can really come to the rescue here. And the second message I want to send is oftentimes these days, particularly in segmentation, we still attach categorical labels to individual objects, but that's rather limiting, I would say. And oftentimes we care about much more holistic descriptions. Like in the bottom, you can see methods that come up with descriptions like a large construction truck with a trailer on it, or a car is driving in the rain on a street, which are much more holistic than just saying, oh, there's a truck and here's a car. And again, this is a second example where foundation models can really aid and augment these semantic segmentations. And as I said before, foundation models really come to the rescue here, and the students did an amazing job here at getting those applications to work. Now, before I dive into those details, let me get back a little bit and set the context right for everyone here. The goal really is to partition an image into segments associated with, at least at the beginning, a set of categories. Like you see the image here on the left-hand side. We want to attach some categories like sky, building, and whatnot. And the obvious question is, how do we actually want to partition an image? What forms the partition? And we have, as a community, looked at this task for decades now. Very early work started in I guess, late or around the 1980s, actually, on semantic segmentation. We eventually moved to a somewhat more challenging task, instance segmentation, in actually not too long ago, around 2010. And more recently, panoptic segmentation on the image side. Something very similar has happened on the video side as well. Video instance segmentation, a fairly recent task. And if we think about that, in 2050, not too long ago, at least in some fields, video object segmentation around the same time, and video panoptic segmentation, again, much more recent. Now, if we look at the methods that have been applied over the years, we see the community kind of jumping back and forth between a set of different techniques. In the 1980s to 1990s, we looked a lot at grouping, and I'm sure for many of you, key papers will come to mind here that have grouping in the title. In the late 1990s, we actually started to play around with classifiers for that task. Early papers, I really encourage everyone to look at those. They're really great to read at this point in time. They simply look at an image and try to classify pixels into categories. 20,000s was a lot about classifying pixels using your favorite algorithm, boosting random forests, structured support vector machines, eventually conditional random fields for people that still know these acronyms. 2010s, we kind of moved back again. We looked again at grouping with mask proposal algorithms. People might still recall methods like CPMC, and I put a few other acronyms there that I encourage you to actually check out. Fairly interesting papers. And then since 2015, we kind of moved back again to classifying pixels. Fully convolutional networks started to dominate the field. Pixels are kind of independently classified with the convolutional neural nets. So it has been this constant shift between grouping, classifying, grouping again, classifying again. And I guess as a community, we haven't quite figured out, is there one dominant approach, or does it really matter? And now looking at it a bit more specifically, if you look at semantic segmentation, oftentimes there we pursued pixel classification tasks. And I mentioned fully convolutional nets. Deep Lab is probably a tool that people that work on semantic segmentation have used up and down. Great work. On the instance and panoptic segmentation side, things were a bit different. There we often worked with object proposal-based methods. Mask RCNN is probably something that everyone here knows. Mask classification, like feature style approaches, I'm sure everyone here is very familiar with as well. And so we do see, while this jumping back and forth that I illustrated on the previous slide has happened, the field of segmentation has also kind of fragmented, that different tasks have been addressed with different types of works. And so one of the things that we were really wondering about is kind of in the spirit of foundation models, can a single architecture address all these tasks? Now, mind you, this is not addressing all tasks. This is focused solely on segmentation. But that was really the question that we were after in these, I guess, somewhat early stages of this research. And that brings me to work on mask format and variance that we looked into around, I guess, the early 2020s with a whole range of collaborators. Thanks to them for a really great work on this. And maybe I'll give you a brief rundown on what we did back then. And mask to format came about based on the question that I highlighted beforehand. Per pixel classification used to work great, and they're very good at processing pixels, and it's very easy to implement these. Instead, on the instance segmentation side, we often had multiple predictions that we worked with simply because we had to deal with multiple instances of segmentations. And their inference was a bit more global, I would argue. But this type of architecture that I'm showing here on the right-hand side could also be used to actually unify semantic and instance segmentation if it were to work well on semantic segmentation. And I guess prior to mask former, people often struggle to apply the technique on the right-hand side to instance segmentation, or at least to perform on par with existing methods. And so we really tried to put this to the test, and students tried to understand what is the real struggle here and can we overcome this. And the result really was, I guess, this mask to former architecture that tried to unify this semantic and instance segmentation words again. There's a backbone, there's some sort of pixel decoder that takes the feature that comes out of the backbone, decodes it in these, I guess, semantic maps. Then there's a transformer decoder, and on the left-hand side, you can see here these embeddings that are actually learned. And these embeddings are then supposed to highlight objects of interest in those maps that are extracted from by your pixel decoder. And then for every one of those masks that we compute simply by an inner product of this embedding, this transformed embedding and the output of the pixel decoder mask, we can also attach a class label. And so this is really an architecture very much in spirit to what I showed on the right-hand side beforehand. And what we were really surprised about and what we found is that this actually worked remarkably well, putting a few tweaks like mask detention in there. And this really led to new state-of-the-art on panoptic segmentation back in those days. It also worked great on instance segmentation, and we could also get it to work on semantic segmentation. So this was one architecture. Back in those days, we still had to train this architecture on every individual task individually, but by now people have actually moved beyond that, showing that one architecture can be trained across these different tasks and still perform quite well. And what we were also surprised about is that this actually worked across a huge variety of different segmentation data sets with a totally different range of categories, from COCO and cityscapes to AE 20K and mapillary vistas. And so that was really exciting to see. Now, the result that I showed before is an example output of the model that we were able to get here. Now, what we were not quite able to answer well, but others did much better than we did, is why did this actually work that way? And here I'm quoting a paper by Fortin and others. Their task was much more challenging than what we ever looked at. They wanted to detect these types of logs that you can see here in those images. And they tried a whole range of different items, from mask RCNN to rotated mask RCNN to the mask to former type architecture that I just talked about. And what they showed is that for some reason, mask to former worked much better. So they really dug in and tried to identify what was the reason. And they showed that mask RCNN, if you don't rotate it, you essentially pull features from I guess, an axis aligned rectangle. And these features are just not very accurate. If you then enable your mask RCNN to kind of rotate, you can extract much more accurate features. However, if your objects are very curved, almost like non-convex shapes, then you still get a lot of features that are not very object specific. And Mask Deformer doesn't really have that problem. It really just, because of the, I guess, transformer architecture, accumulates the features of interest. And those features get more and more accurate as you go through that transformer stack. And that, at least according to their studies, had really improved results. They were able to address fairly challenging tasks. I was actually surprised seeing the results that this seemed to work rather well. Now, obviously, we don't want to get stuck with images, right? The immediate next question is, how about videos? We all live in a time domain as well. And just applying that in a straightforward way to videos actually enabled to get fairly accurate results as well. We didn't really make any changes. However, I would also argue that this is probably not really the way to go there. Because while this works within a closed vocabulary set, you often need this end-to-end training on actually video data to obtain these very accurate results. And that's just very demanding to really obtain. So suppose you talk to some collaborators, they show you a video like the one that I'm presenting here, and they ask you, can you segment this for me? Can you detect and track what those piglets that you can see here? And so how about we try to do that together? Right? What would we do? The first thing we do is we go to GitHub, right? And we look for some pre-trained and open source models. And the next thing you'll find is where all these models that are out there, they're trained on data sets like YouTube VIS or OVIS, for instance. And they have a decent amount of categories, right? YouTube VIS, 40 object categories, OVIS, 21 object categories. But unfortunately, they don't have pigs in there. And so we're kind of out of luck. Dogs, sheep, tiger are probably the closest in one data set, cow, fox, duck, the others. But there's not really any pigs there. So what can we do then? Well, the next best thing to do is, well, how about we collect our own video data? And that obviously becomes very time consuming, takes a few months, and it's just not rewarding for anyone who has ever annotated data. So just not very convenient to do. And then your collaborator comes around 4 months later and says, now I have a new object. Can you help me do that again? And you're like, wait, should we annotate again all this data? Right? It's just not scalable. So we need to find better solutions, I would argue, that actually can scale. And that gets me, I guess, to the second point of, beyond densely labeling videos. And what can we do? And again, credit goes to an amazing set of collaborators. And so there's really, I guess, two main paradigms here on how we could address this. We can go with the mask propagation-based approach. We can run image models, and there's amazing image foundation models that we can benefit from and take advantage of. Or we can go with a mask propagation-based approach. Let me start with the latter, and then later on dive into the former. So if you talk about mask propagation, I'm sure what comes to everyone's mind is tasks like video object segmentation. And it has been a task studied for quite a while. We usually take as input a video frame and a segmentation mask for the first frame, as you can see on the left-hand side. And then we ask a model to just detect, track, and segment forward for all the remaining frames. And there is a decent amount of training data for that type of task. And we can do a reasonable job at that. There's amazing models. And what those models often fail to do is they are, I guess, over-indexing, I would argue, on the pixel side. So one of the things that we try to look into is, can we better capture what constitutes an object and memorize how objects change? So one of the things we did is incorporate some sort of memory architecture into these types of models. So then we get the query frame, we have some transformer-based lookup into the memory, which then gives us the corresponding features. And by mixing those with the pixel-based image features, we then get the output. Very similar in spirit to the mass-to-form architecture that I showed before. The one addition is now this temporal memory that's incorporated here. Some technical terms attached to those slides. We can skip those in the interest of time. Here's a bit more detailed architecture of how this memory looks like. And what we really took inspiration here from in this work titled XMEM is the memory model that neuroscientists Atkinson and Schifrin proclaimed is what the human brain is also based on. They're essentially saying there's 3 tiers of memories that work as humans, often using a sensory memory, a working memory, and a long-term memory. And we try to get into these deep net architectures a similar structure, a sensory memory that is essentially very short-term, looking at one frame to the next. A working memory that's a bit more long-term, kind of on the clip level, if you will, and then a long-term memory that can really allow you to keep in mind objects that you have not seen possibly for a very long time. And so the sensory memory, as you might have guessed, classic approaches, some GRU or transformer-based approaches, nothing fancy here, very sensitive to loci. Working memory, I kind of talked about this already, updated at slightly lower frequencies, but somewhat more high resolution. Has a capacity about a few seconds, and this is usually what the average clip length is like in any meaningful video. And then the long-term memory, which is updated when essentially the working memory is full, it tries to consolidate those features and enable the model to get back to objects that it might not have seen for quite a while. We make sure that all this is implemented in a reasonably effective manner. And here's again the result that I showed before. Let me start this video. As I said, you will start off with a mask for the first frame, and then the object can detect and track these objects. The video is now sped up a bit. You can see it can track these cans even if you move them outside the frame. You bring them back. You can even move them outside the frame one by one. You can hide them below the towel. Now this is the interesting part. Now we hit them under the towel. We play with a scissor for about 1 minute. The model doesn't see the cans for pretty much 1 minute. We look at Rex, my student, playing with the scissors and the banana, eventually getting back to the towel, rotating it, making it a bit more challenging, and then lifting the towel, and the model still recognizes the cans and can detect and track them. And this is really enabled by this long-term memory that keeps these features in mind and enables the model to not lose track and lose sight of the objects that it has seen before. Some numbers, you can also look them up in the paper. I don't really go through those. I think what's particularly interesting is the column that's titled Long Video 3x, really demonstrating that, particularly on long videos, models often lose track of these objects. And by incorporating these types of memories into your model, you can do rather well on this. Here's another interesting plot. Maybe if you focus on the one on the right-hand side, you can see the diagonal axis, which shows the performance or the diagonal line that's dashed and gray. And then the y-axis is the result, like JNF result on short videos, and the x-axis is the accuracy on long videos. And so the diagonal line is essentially equal performance on both short and long videos. And the majority of the methods happen to be on the left-hand side of the diagonal line, meaning they perform very well on short videos, but not that well on long videos. And by incorporating that memory, we can really shift the performance of these types of models to the right-hand side, which was very exciting to see as well. Some more ablations. In the interest of time, I'll skip those. And I want to now focus on beyond user annotated frames. And this is really where the foundation models can really help us. is one of the annoying things of what I just talked of models that I just talked about is that we need users to annotate the frame. Now imagine I go to my collaborators and tell them, for every video that you have, you need to go in and annotate that first frame. They'll not be very happy about that either, despite the fact that it's much less annotation already. And that brings me back to this picture that I showed a while ago, where we also have these image models, and we have remarkable progress on the image side, particularly on the foundation model side. And we can incorporate that via techniques like tracking by detection, which have been studied for quite a while too. Obviously, they have some cons, like they're very sensitive to detection errors. They use limited amounts of temporal information, and these cons is exactly what I'd argue we need to address in order to improve results. Now, talking about some of these foundation models, I'm sure all of you have used them in one way or another: clip, segment, anything, grounding, dino. There has been a lot of progress in the last couple of years. And we want to, on the segmentation side, benefit from this progress and really help our collaborators get really good results in the sciences domains that they care about. So grounded segment anything is for instance, one example. And the real question here is, how can we extend this to the video domain? How can we benefit from all this progress on the image side and transfer that to the video side as well? And there's obviously the classics that you can think of, right? Can we combine these image segmentations with essentially the mask propagation-based approaches that I just talked about? And that's really what we focused on for the majority of our work. So here's an example of what we would care about. Suppose we want to segment any object in a video, and we want to guide the model simply by text prompts. Right? That would be ideal for collaborators. They don't need to tell me what types of objects they care about ahead of time. They get the video and they specify via a text prompt, here is what I care about. So video on the left-hand side, I care about segmenting children, the toy car, and the bicycle. And then we want to get the result like the one that's illustrated on the right-hand side, where we accurately detect these types of objects. We can segment them and we can highlight them. Now, how could we go about doing that? And this is really where the amazing progress of foundation models comes to the rescue. And we can take the input image, feed it into something like a grounding dino type model where we have text content and gives us the bounding boxes. Based on those bounding boxes, we can now feed them into a segment anything style model, get the segmentations out of it. And now we need to incorporate the time axis too. And there we have frames segmented one at a time, but we don't have any associations across time. We need to establish these associations, but we need to do so reliably. And just as I will show in a bit, if you just naively run and establish associations in a straightforward way, you will get very jittery and very noisy results. And this is where this, I guess, box labeled debug comes in, where we really try to get good associations across time from these models. And I'll talk a bit more what is inside this box and unwrap it. And the final result is the one that I already showed, where we can detect, segment, track objects fairly accurately across time. And I also show more results on those pig videos later. So how can we go about then incorporating this? What did we find to work well? So applying the detections one frame at a time is a good starting point. We now use this a memory-based architecture that I introduced in the previous part, and kind of work this forward or propagate the masks forward one frame at a time. We can continue to do that for quite a while. Every now and then, we now run this grounded SAM model, and we then try to merge the results, the propagation results, with the detection results. And the key really lies in how to do this merging rather well. A straightforward approach would just run this detection model every n frames. You then use the image detections and merge the detected segments with the proposed with the propagated segments. Using a couple of rules, segments that agree are merged. That's fairly obvious. unmatched detections are added as new objects. That enables you to essentially deal with new objects that come in, and unmatched propagations are passed through for a while, and if you don't observe them for a certain number of times, then you just drop them. Works reasonably well, but maybe not quite. And here is one result that from collaborators that we then got back, and that's obviously not quite satisfying. Objects get merged. It's not as robust as we would have wished it would. So can we do better than that? And this is where we then thought about essentially getting some consensus voting into the mix. A single frame detection might be quite noisy, but the consensus from multiple frames in short clips is less noisy. And maybe this is an avenue for folks directly working on foundation models to still look into and improve upon. How can we get better consistency across frames? I think a fairly interesting and exciting topic, something that's beyond the resources that we have available. But that means we kind of moved around the boxes a bit. This was the architecture that I showed before. We now shuffle things a bit around. We have, again, our propagation result instead of running a segmentation. Oh, there we go. Instead of running the grounded sound once, we run it a couple of frames, perform some consensus voting, and then we merge the results back. Now, how am I doing on time? 5 minutes? Okay, great. Then I'll speed up a bit. How to find this consensus? I skipped through the details here. I encourage you to check this out in the paper. And the short answer is we'll solve some fairly lightweight interlinear program. Yes, not that popular anymore, I suppose, in this community, but actually works rather well, I would argue. And it is rather quick too. Plus, during training, you can actually backprop through that as well. And that turned out to give us rather reliable results. Here is the result that actually collaborators were very happy with. Then the input is the video, and the prompt I care about pigs. No one has to go in, annotate the first frame. Also during training, we don't have to annotate pigs at all. And keep in mind, as I alluded to at the very beginning, pigs don't exist in classic computer vision benchmarks. So collaborators were very happy with seeing that result. Now, as I predicted beforehand, not only were they interested in pigs, soon they came back and were interested in segmenting capybaras. Don't ask me why, but they were interested in that, and the model works out of the box there too. Here's another example. Guinea pigs and chickens was the next thing they were interested in. And we found the model to be surprisingly effective at extracting these objects, segmenting them, and tracking them. So foundation models really helped us address this task. And I would argue made these tasks much more scalable than they used to be. Scalable in the sense of the data that was required to address these tasks. Another example on a more classic benchmark, if you're interested in people and trees, model does a fairly decent job at that too. Brief shout out to Rex, the student who did this work. Really great work, I would argue. You can talk to him Wednesday, June 19, posted session 1, R4A to E, posted 291, I believe. There's a project page out there too for the 2 works that I actually mingled into one talk. There's code out there, everything is public. You can go use it, try it on your data. If it doesn't work, reach out to us. Very, very happy to help you get this going. So summarizing or wrapping up this first part, it's very user-friendly because only text prompt is needed at this point in time. You don't have to go in and annotate anything yourself. And foundation models were really enabled us to go beyond user annotated frames. Now, in the remaining 3 minutes or so that I have, I briefly address the second part, beyond simple categories. As I mentioned at the very beginning, we don't just want to attach some sparse categories to these objects. But I would argue oftentimes we want to go way beyond that and get much more detailed descriptions. So instead of a result like the one that I'm illustrating here, where you have a sequence of images, a video, and you attach labels like car, pedestrian, 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 and so on and so forth, and then maybe some foreground and foreground because you don't have that object in your database. What you'd want is something along the lines of what you see here on the slide, where you have a car driving down the street. Here's another car driving down the street. A woman is walking down the street. There's a man with a crutch crossing the street. And a woman is standing at a red table by the side of the street, and so on. So I would argue this describes the scene in a much more holistic way. Now, how could we go about do that? And I guess the surprising answer again is, well, we need to get these classic computer vision tasks and hook them up with foundation models. Now, I'll not walk you through the details of this entire diagram. Suffice to say that within this, we have two what we call abstractors, which essentially translate from one space, the visual feature space, to another space. The next space is the space of object queries, and then we take these object queries and translate them to what we refer to as the space of text queries, which gets then used by a frozen large language model to describe the scene. And the key really, I think, is to design these abstractors, these translators, these units that transform representations from one space to the other space very well. And I believe as a community, that's something where we still need to spend quite a bit more time to understand how can we design these translation units, if you will. This is a very first attempt at this. It is unpublished work, but I think fairly interesting still. In this object abstractor, there is some sort of prompt encoder that takes a set of grid points such that you get features from pretty much uniformly across your images. This is your open world representations. You have some closed world embeddings that you have also trained. Feed them into the transformer decoder. Again, very similar to the master format that I showed before. And you get open world and closed world queries abbreviated with OW and CW. You then feed them into some object to text abstractor. I'm very happy to talk offline about the details in that one. The output of which is essentially a representation that the language model can then use and translate into a more holistic description than just a category label. In this example that's illustrated on this slide, a rabbit sitting inside a box. Now, evaluating that, what we observe is that this type of model does rather well, again, on the unseen category. So objects and types that you have not seen during training. And that's obviously in part because of this interaction with the large language model that can attach accurate descriptions to that. We're suffering a tiny bit on the seen categories, but overall not too bad, I would say, at this point. Similarly, when captioning, the result actually does remarkably well. And I do want to highlight that this is an online method, meaning it operates in a streaming-based manner, as opposed to an offline method where you have to take your video as a whole as input and then process it. Results are the ones that I illustrated at the very beginning already. So in the interest of time, I just skip through those. Conclude here by, again, saying that foundation models enable us to generate more holistic descriptions. And overall, for my entire talk, I would say foundation models really permit us to address exciting new tasks that can really advance the field beyond what we have looked at so far. There's still a lot of work that's needed, for instance, on designing these translation units that help us translate between these different tasks. And I would argue that that's an area that's quite underexplored. There's a lot of opportunities to do exciting work in this domain. With that, I'm going to thank you for your attention. I'm going to thank my collaborators for again, great work. I thank all the people that provided funding to make all this possible. And I'm very happy to answer any questions now if time permits, or I'll be around at this conference. Just ping me, drop me a note. Very happy to chat. Thank you.
Thank you. So time for some quick questions. Okay, so I will just start with one very quick question. So you mentioned how XMeme also works effectively for long videos. So can you please describe how long those videos were? I mean, because the data set that you used for this long video understanding is only 3 videos, I guess. It's the Generative paper. So how extensive that was that experiment?
Yeah, that's a great question. We did actually fairly extensive experiments on that. So you might have seen on the slide somewhere we wrote there was a 3x summary. So one thing we did is we took the video and we then reversed it, added it, and then used that 3 times to make the video longer and to really assess the performance. But what I do want to highlight as well is in this model, the memory is actually bounded. So we really made sure that the long-term memory, the working memory, and the sensor memory have an upper limit. And what that enabled us to do is really to scale to videos of any length. Now, obviously, it's what we haven't tested, and that could actually be an interesting experiment to do, is what happens if you see an object initially, and then you don't see it for a really long time, say 10 minutes. What we checked was, if you don't see the object for 1 minute, that worked rather well. But what if you go way beyond that? And I suspect there's also quite some interesting work that could be done in that space, is features might get forgotten in the long-term memory down the road as well if your video is really long. So that's another interesting opportunity for more work.
Okay, very good. So any other question? Yes, please.
Yeah, excellent question. Question was, what are the failures in the XMeme? So collaborators really challenged that model. For instance, they wanted to detect pigs at night. And that's something the model really struggles with, for instance. So then shadows become pigs, or shadows and pigs get merged, for instance. So low light situations is, for instance, one thing that the model really struggles. Also, if there's a lot of very similar objects. So for instance, collaborators, they have videos showing piglets huddling together, like tens of them. And the model cannot in detail extract any of this. So if they have, say, if objects have very similar color and are all very close together, XMeme still struggles with these types of situations. For foundation model type works, I think the models they are struggling with situations or data that hasn't been seen by these types of foundation models. So for instance, if you look at microscopy data, or other collaborators that we're working with, people that want to detect or neuroscientists that have certain types of data. Foundation models don't perform very well on these types of data. And that's another failure mode that we see. How to exactly address those is again, great question.
Okay, so let's thank the speaker again. Thank you very much, Alex, for a very interesting talk. Okay, so now we will be moving to our next speaker. Okay, so we are ready for our next talk. It's a pleasure to introduce Irfan. Irfan is a distinguished professor in the School of Interactive Computing and a senior associate dean in the College of Computing at Georgia Tech. He's also serving as an inaugural executive director of the new Interdisciplinary Research Center for Machine Learning at Georgia Tech. He also serves as a senior staff research scientist at Google.
Just taking away my time from speaking. Sit down.
Yeah.
Sit down.
So it's a long one, but I will keep it short, Irfan, for the time. So his works in the area of computer vision, machine learning, computer graphics, computational perception, robotics, computer animation, and social computing, with potential impact on autonomous systems, video analysis, and production and human-computer interaction, to name a few. He has been awarded the NSF Career Award and also elected to the grade of IEEE Fellow. He has also extended research consulting positions with Disney Research and Google Research, and also an adjunct faculty member at CMU. So it's a pleasure to have you, Irfan, here for this talk. Thank you
so much. People can hear me at the back? All right, so okay, I like to move around a lot, but I'm going to try to stay there so you can hear me. So of course, we're talking about foundation models, and I just realized that there are at least 5 workshops going on foundation models just today, right now at this moment. I'm going to talk a little bit about foundation models, but mostly I'm going to talk about is approaches we can kind of bring to bear that could form foundation models in the area of generating content. Just to situate this, first, I'm an old guy. I've been around in the field, and that I need to figure out a short-print ChatGPT version of my bio. But been interested in really understanding content to help generate content. So lots of different examples of that kind of stuff over many years in this space. And again, this is all the pre-foundation models era, but there's a lot now we can do in this space. Today, I'm going to give you a little bit of sense of some of the work that we can do and how we can use these types of analysis of content that can then be used to generate content, that can be used to generate images with style, videos, and also thinking a little bit about some of the challenges of this kind of stuff. I like to always kind of start off with like a little bit of thought process to what's going on. So one of the biggest things that's kind of going on these days is trying to make it so a lot of people can generate content, right? Everybody wants to, we're on social media. We're in the era where we want to democratize content creation. So that's where an interesting phenomenon is coming. You can all capture images on your cell phones. You can also do a lot of content generation on cell phones. And the whole paradigm switch that's coming is, in the old days, we took a captured image, but now we can generate images at the same time. We'll think a little bit about that too. But also what's really happened is this whole wonderful world of machine learning, where we can now basically train a lot of things, basically do implicit training on different types of things. And that helps us do a variety of things. But there's still a little bit of a dark part that's associated with it. How you build models is how you train it, how you give it the right kind of data, and also sometimes the magic parameters and all of people like you folks, students in the room, and others who've been doing this research to learn how to do. But that's an important part of it, how to make these things repeatable and robust. And the final thing I always like to kind of point out is, in this world of understanding content, we've actually gotten to this really interesting thing that while we started off with just sentences being completed, now we can write full documents and also make generated videos and stuff like that. Simple things of understanding data, which was a key part of even things like autocomplete. And that's why, computer vision in the world of images is still an important part of what we do. Before we start, I wanted to kind of set the stage a little bit of, caution notes. Here's one. I'm going to oversimplify a whole lot of concepts today. Similarly, I'm going to talk a little bit about ongoing work. Then also, this is phone a friend. I'm not going to get into technical details. There's a lot of people who have worked on this kind of stuff. If you ask me a hard question, I might have to phone someone. This talk will have no tables, no bold entries telling my work is better than those, because apparently as reviewers, all of you, that's the only thing to look at in review papers, is a column or a column with a bold number. And if you show a lot of those things, you won't see any of that today. And then, of course, the wonderful world we're in. This talk is pretty recently done, but I can assure you it's pretty much outdated, the way things are being done these days. That's the fun part of it. There's even stuff that I have that I'm not going to talk about. It's so recent, I haven't had the time to put it in my talk. Lots going on. Good number of people that, as I said, if you ask a hard question, these are the people who can answer it. I have the privilege of working with some amazing set of people, both at Georgia Tech and Google. So also just a list of papers, you can look them up also on Google Scholar and stuff like that. So let's get started. What's going on in this world of generative models? Of course, we started off with a lot of technologies trying to basically understand variation in autoencoders, GANs, but then came diffusion methodologies. And again, it's all recent, right? Variational encoders are 2014, generative GANs were 2014 timeframe, diffusion models 2015, but then really kind of hit the stable diffusion with 2022. And 2017 is when transformers, which were actually the kind of foundational work on large language models, started coming in. And now, all of a sudden, basically, what we have is a very set of tools that enhance your productivity of generating content. Again, remembering by actually having annotated and clear data of what you're trying to learn this from. One big debate that we're coming into, and actually today you just have seen at least 3 or 4 workshops talking about just diffusion models and stuff like that. Lots of conversations going on. One, of course, transformers versus diffusion is becoming choice that majority of us have been dealing with. And I'll show you examples of that in this talk also. One, of course, transformers were really driven by language models, or at least some sort of tokenization strings and stuff like that. Diffusion was really much more at modeling the phenomenon and actually reducing the data that you could look at different levels so that you could actually understand them or at least generate them at different levels. Of course, both of them can be paired with some sort of a large language model and do text-to-image generation or text-to-video generation types of things. And again, we'll see examples of that. But the key part of it was, and I think you also saw this in Alex's talk, was one of the biggest questions and visions we've been interested in is, if somebody gives me a picture, I want to generate a text string for it, right? That's what many of us have been doing this for decades, many of you have been doing it for a while. Give an image, I want to be able to generate a text parse of it, saying what was in the scene understanding question, age-old question. Now we're in this, using these transformers in diffusion. The question is, somebody gives me text, and I want to be able to generate a picture or a video or something much more complex than that, sequences and stuff like that. And there are bigger questions as to what level of granularity should that text have. As we also know, this picture to text question, there could be many different text strings that best represent that image. Granularity, if you ask somebody who knows about birds, they'll tell you about the exact details of the birds. And people like me will say bird on top of a flower, something, so different granularities exist on this. So let's build on that kind of concept and start asking the question is, how can we start generating images? Of course, it comes down to is being able to understand this. But before we go there, I want to give you a little bit of a primer of where we have been going in this world of text and synthesis of images and stuff. I mean, people have been interested in generating images for a while. Before many of you were perhaps born, there was a movie, Star Trek, The Wrath of Khan, which was basically about how they actually synthesized the whole Genesis effect of the planet kind of having, different types of terraform and things. Very procedural models were being used. Procedural basically means I come up with an equation and I give it some numbers or some parameters and it generates different types of things. Of course, initially we started doing this with textured images. This is where Heger and Bergen types of things came in, is looking at these types of models, we can actually generate it. Then actually came this other idea is we can start using patches, not the whole pixel strings itself. When you can take those patches and splice them together in space, and also perhaps in other ways. And also this concept of painting different types of things came in. This, of course, was all extended to be able to do this for videos. We can now generate spliced images and videos. We didn't have to just do splices at the frame level. We could do it at the surface level through the volume of an image and stuff like that, and graph got supported. But again, this was taking pixels and regions and patches, merging them together. And this led to, before this whole world of content-based image query types of things, this whole other effort of content-based image synthesis. Now I can say, taking Alex's example, 5 piglets watching next to a pool, we can generate an image or a video of a piglets walking around. So that kind of, again, knowing piglets is important. And this came into much more larger scale by doing things like hole filling types of stuff. We can take an image, I would say it's okay, fill this out, cut this out, and put a water scene differently and stuff like that. And this led to more work on really doing kind of creative things, like deep clean types of things. This is again 2015. You have seen so much progress in this in the last just 3 months that is mind-blowing. One of the insights on all of this always has been is this whole concept that you want to take an image and extract from that some sort of a string, a token string. So take an image and define as a set of tokens. And one of the things that this paper actually allowed us to do was not just kind of do this for the entire image, but create some random masking. Now, you might remember that's one of the biggest things with diffusion, right? Diffusion was kind of taking different things at different frequencies and being able to show things at both low res and high res. Transformers didn't allow this in the world of images because they were doing sequential parsing of the whole image. And this work, basically the idea was, well, let's do visual tokens, but create some sort of a random masking to be able to reduce the amount of content. That actually helped with scaling things quite a bit. So this was the work on Muse, which basically allowed us to now basically do this kind of a process to be able to take images, or sorry, give text that knows these tokens and use this to generate images. And of course, was much faster. Part of this was, again, a tokenizer and a masking system, and then a bidirectional transformer that would take this and come up with predicted tokens to generate images. I'm going to go through a whole lot of this fast. There are lots of papers on this one that you can look at. But again, you can take input images, define weak tokenizers, take mass tokens, and generate this, build a base transformer, and also do this at multiple resolutions. So get super resolutions to be able to generate larger images. And now you can just type in things like this, and you can generate beautiful looking images, just even photorealistic ones, artistic ones. You've seen many examples of this with DALL-E and others online. Midjourney has applications of this kind of stuff. So this is just a different variant on this one. We have actually also taken this kinds of stuff to do something much more applied with this. So you've seen things like your magic eraser and stuff like that on your cell phones, where you can now basically fill in things. Oh, microphone died. Hello. I can speak loudly for those people at the back. Can you hear me still? Okay, it works now? Okay, yeah, something died. So this is an example of now, once we have these types of models, I want to be able to do, among other things, backfill to get rid of objects and stuff like that. So this is something, again, now is running after the model has been built, running on device in a Pixel 8 thing, where you can now do things like remove larger objects and it backfills it perfectly well. An example that is shown here using the technology that I showed. These were pictures I took while I was at ICCV last year. Previous versions did not do a very good job of removing some of those details, but if you notice, the Magic Eraser version 3 does this quite well. We can get rid of unwanted family members and stuff like that very easily. And again, many different examples of this exist, and we'll just go through this fast. The other part of it was sometimes when doing these Magic Erasers, the other thing that you needed to do was if somebody was holding an object like a bicycle or an umbrella, you would remove that person, but you would not remove connected objects. This thing again detects those connected objects and can remove those types of things also. So now you don't have these unconnected things in the scene. Just an example that now you can go to dinner with lots of people. We don't like them, we can get rid of them. And again, this is running, but it is actually using these generative models on device now with a small model running in real time. We can start playing around with this to start doing style. Now, here's a simple example. I want to be able to do fine tuning now. So that is that we've built this model, and what we want to do is find a few examples and say, make me images that have this kind of a style. And now that I say bird with this style or a dog with this style, it starts rendering these types of things based on, again, the fine tuning on the Muse type of model. Many different types of details. I'm going to skip over this, but again, the same architecture that we talked about before with the tokenizer, except that this time around, we add another layer of fine tuning that allows you to take more input of specific things, and it could just be one input, not more than, sometimes more than one, but one is sufficient to do this. And again, we changed both the base transformer, deal with attention mechanisms on that fine-tuned images. To be able to do this, I'm going to run through this quickly, but here basically now says is, okay, I have a style reference image. Using this, now I can generate all kinds of other characteristic things that have that style. And again, there is a new version of this one that's out too now. Here we see six examples to generate these things, 6 examples. Just a simple painting can generate more examples that look like it. This is one of my favorite examples. I always talk about it. This is Kehoe's niece, the lead author on this work. He had her paint this small flower garden with just her crayons. Just using that one example, we can generate a wide variety of stylistic things driven by that. Again, application of a foundation model after it's been done with these things. We can generate textings, a whole lot of things. I'm going to do this, but and the bottom line is it is actually now also running on the Vertex AI on Google Cloud for some of our clients in that area, and also was just recently showcased to be able to take even the story of the Alice in Wonderland developed by different people with different styles. Again, using the different artists use their own styles to generate the visual conditions of these types. So the power of these types of things becomes really apparent. Let's move to world of video. So same kinds of things, except this time around, we want to take the masked model and apply it in space and time. So which basically means that now all of a sudden, our tokenizers are no longer, token strings are no longer just image pixel regions, but they are spatial temporal volumes over time. And again, you have to do various types of optimization. This becomes a uniform model that could be used for frame prediction. You give it one frame, it will predict the next set of frames. Frame interpolation, you give it 2 frames, it'll figure out what's in between those, because it's learning those models and actually interpreting. This is not doing text at all at present. You can do outpainting, you can do in-painting, and you can also do things like just give it an act, give it a scene and say, okay, I want this kind of an action performed, like squeezing something. And it would actually do these types of things by, again, looking at the token strings, find the best possible things and generate. This was actually a paper last year in CVPR, if anybody's interested. Because of lack of time, I'm going to quickly go through this, but again, here's the example that we are actually doing 3D vector quantization to create volumetric models, and then we take the same kind of bidirectional transformer to be able to generate this, and this can be done at, in this case of the work here, 240p real videos, and being able to do this. It also provides various forms of compression, so almost 600 times in smaller compression, because we can take those token strings to be able to generate things whenever we want. More details on this one that I'm going to skip, but basically this kind of starts giving you the framework that now we can actually start doing this at a various sampling processes. Again, allowing you to do these random masked scenes over space and time to be able to generate this. Again, lots of examples. We can do frame prediction, frame interpolation with this thing, outpainting, in-painting, central things. And again, lots of different types of things. One framework that supports all of this kind of stuff. The examples of them we can basically use is giving one frame of this thing from your panoramic, we can generate a full panoramic video out of this stuff. And more examples of the same thing. You scan through with your cell phone, and you can generate a full video at a much better resolution and a different aspect ratio. I'm going to skip through a whole lot of this. I have loads of examples. When you work on video, you have loads of examples across the board. We can do actions and stuff like that too. Of course, if you notice here, while we can interpolate between different types of things, camera movements are a little problematic unless you figure out how to incorporate that kind of stuff too. I believe there are 2 workshop papers that actually do camera movements based on this technique this week also. Again, skipping through this, as you've seen already. So now also build it. We've actually then, since then, this was last CVPR. This year in iClear, we've actually added more text information to this one to do text encoding. So this is Magbit version 2, where again, we're taking the tokenizer, but merging it much closely with the generation processes and actually incorporating the large language models much more appropriately. And this helps us create this new system called Video Poet, which is a large language model for zero-shot video generation. I'll show you examples of this one, but you see basically, again, is by just now doing text encoding, we can generate different types of viewpoints from one frame and then adding more information from it. So this is mostly an example of image plus text to generate videos. I'm going to skip over this, but the same kinds of frameworks, but actually in this case, we also deal with a lot of audio signal too, to be able to do it. And then you can generate things like this just by giving it a text string, panda, mad scientist, sparkling chemicals, art station. And again, You've seen other examples of the same kind of technology online from other players in the space too. But you can now start seeing we can generate quite good resolution videos and things like this. I mean, here you notice the physics of the water. It looks also good because it has seen a lot of videos of water. And of course, the moistness and stuff like that. Now, for those of you who are really picky about these things, you will see some of the texture does float. Some of us who are in this field, we can notice those differences really quick.
In the Amazon raccoon forest lives Rookie the raccoon and his family. Rookie loves to play soccer with his friends, collect acorns from the trees.
Another example, so now so far I've talked about tokenizers and transformers and stuff like that. You notice when I actually talked about how we actually did the mass encoding, it kind of generated a representation of masked regions over time, which kind of is where the latent diffusion models are very close. So in this work, we combined the whole tokenizers with latent diffusion to be able to generate much more effective, much more efficient video generation, which are also much faster, compact. So this is, again, another whole model that we've been working on. This is work that's actually out there. It's not fully published yet, but it's on archive. I'm going to skip through all of this, but the idea really is that we want to be able to compress images and videos in a unified latent space. That's what Magwit version 2 gave it. And then we actually created a windowed attention latent transformer to be able to incorporate this, to be able to generate types of videos that I'll show you. Architecturally, again, lots of things going on in this space about trying to, how do you figure out, how do you find the right kinds of attention layer to be able to mask this correctly to generate. Again, I'm skipping over the details because I want to show you some of the results. This is now modeled that was used to generate text to video samples at certain resolution. This is about at 8 frames a second at, and these are 3.6. And again, this is about a year-old work. But just by doing this kind of stuff, you can see much better resolution content like text input. And again, you see the physics, you see motions and stuff like that. There is advances that have come in. This was a work that was about November last year. And you've seen other work that's been publicly demonstrated by lots of people since then. We believe this is one of the first few efforts that kind of showcase how to do this on data. Yes, if you start looking at it carefully, you will start seeing some sort of motion, issues with it. Actually, some of the newer versions have actually dealt with these types of things too. And I think the ice cream one, it basically shows that, even things like dropping caramel works very well in these types of things. Again, it was simply just being able to generate this from text in. Here, we are showing some examples of camera movements, and here you can see the camera aspects are actually maintained, or at least the viewpoint ones are maintained, which were not in the previous slides of things. This is a set of examples. Given one image, in this image, the images were generated by using DALL-E version 3, and then we added a text string to be able to give it a little bit more dynamics to it. Here you can see camera motions, even animations and stuff like that. So really complex set of motions. I mean, the water flowing is good, and the reflections and all of those things also coming in pretty reasonably well. So more details on this website if you want to look at it. I wanted to also kind of just close out very quickly with just a few things that, yes, when you start getting into this whole world of images that could be generated or videos that could be generated, we have to be very responsible. I know today there's also a workshop, I think today or tomorrow, on detecting fakes. This is getting into a pretty complicated world right now. As you can see, these can be really complicated. There's a lot to be worrying about these types of things. And I know, at least in my field right now, I have to be careful when I give talks like this, that yes, there are people worried about their jobs. People are worried about copyright, plagiarism, and all that kind of stuff could be used for misinformation and stuff like that. Lots of challenges are coming in because this is actually kind of where it gets into the debate of what is AI. So just to be thoughtful of, and the reason I wanted to kind of say is this is something which actually has been going on for a while. And when I talked about this whole word on content-based image creation, you can do content-based image editing. And this is really old work. We've been doing this for a long time, where you can take an image like this and find clouds from other scene, and just now by other text or click and stuff like that, generate a completely different, yet a subtly different image with a completely different message, right? So this is all of a sudden starting to know dark clouds mean different types of things. This is very subtle. You can do this really not subtle yet. So the challenges remain in this space, and being able to kind of play around with this, we need to be very careful about. With that, I just wanted to kind of say again that I'm kind of motivated by 3 different cartoons here of trying to say is that, yes, we're actually making some amazing progress. Technology is actually much better now than it was. Actually, we need to be very careful about how we're impacting society. With that, thank you. Any questions? Thank you.
So questions?
Lunchtime, I know. Yeah.
Yes. So thanks for a nice talk and showing so many interesting examples. Still, if you look at state of art video generation models, there are still like, a lot of inconsistencies we see in terms of like increase the probability of model. How do you see, like, going forward, some of those limitations can be addressed?
So one of the hypotheses of our recent Walt paper was, give it more data, it can do much better. And actually, at the same scale as you give the data, this data actually helps you get the better. So one answer, of course, a top-out answer is more data. But more data with appropriate types of annotations. Once we're getting so close to the end, the challenge of reality is becoming very important. So for example, what happens with physics? I mean, I can show you some examples where splashes and all that stuff are actually physically correct. But if I was to model the fluid dynamics of it, are they? So this is where actually now can actually bring in real physical dynamics simulations to train in the model to improve the quality. The hypothesis is give it good data, it's going to get better. Can we get good data of real physical phenomena? It's going to get better. The reason it's actually doing well in water types of things, there's a lot of examples of water online. But not all physical parameters or physical existing things are actually modeled correctly. Things that it has had problems with, and all image generation problems happen, is with things like counting, which also applies to things in the world of physics, is that what is the physics of the bouncing ball? How do you model that kind of stuff? So more data will help, but at the same time, there's going to be additional level of fine-tuning that we need to do to improve on that kind of stuff. So one, of course, is more data. The second layer is going to be is how we can actually do fine-tuning with better annotations to kind of close the loop on it. And that's something we need to start kind of thinking about. Now, having said that, I will admit, person who works in this field, I have actually been surprised how even in the last 6 months, some of the videos that we're seeing are actually showing better physics than I predicted. So somehow or the other, these models that can encode this information, and we give it a lot more data, would actually do the right thing. So an example is, when you see a car, you always see it on a road. Whenever you want to generate a car, it's going to actually generate it on a road, not flying. Why majority of the time it's actually seen a car on the road. So that other form of data is going to also balance that. All right, anything else?
So no more questions. Let's thank the speaker again. Thank you, Irfan, for a very nice talk. So with that, we conclude the first half of this workshop. So we are going to go.
So good afternoon, everyone. Welcome back to the second workshop on foundation models. And for this afternoon, the first keynote talk is by Professor Yu Liang. And Yu Liang Liu is currently served as a full professor at Huazhong University of Science and Technology. And his research program focus on vision and language processing with a special emphasis on the document analysis. He received his PhD from the South China University of Technology. and he was published more than 60 top-tier papers on the such as Super and TPME. And since this is midnight in China, so Yu Liang has pre-recorded his video. So let's play in the video of Yu Liang.
It is an honor to be here today to present on our multimodal large language model Monkey and its application in document intelligence. My name is Yuliang Liu, and I'm from Huazhong University of Science and Technology. Let's begin by discussing the research background. Nowadays, artificial intelligence is a primary focus for many countries, including the US, China, and European nations. As Mark Zuckerberg stated during Meta's 2023 earnings call, building the most popular and advanced AI products and services is a clear long-term strategy for Meta AI. And I strongly agree with this perspective. Large language model technology is also considered a strategic high ground by major corporations. We can see numerous large language models from various companies such as OpenAI, Baidu, etc. And these technologies are revolutionizing the capabilities and efficiency of artificial intelligence and human-computer interactions. In the first half of 2024, AI-centric startups raised nearly $50 billion in funding, outpacing overall global investments and financing growth. The United Nations Conference on Trade and Development also published the Technology and Innovation Report 2023, which highlights AI's impact on trade and development. This report discusses how AI can drive economic growth and underscores the importance of international cooperations in AI development. Just as we witnessed numerous applications in industries and academia in the last decade, large multimodal models today have the potential to bring significant benefits to our daily life. So what are the large multimodal models? Essentially, large multimodal models are quite straightforward. They excel in two main tasks. First, given an image, they can generate a detailed description of it. Second, they can handle visual question answering questions, tasks, where they respond accurately to questions about the images. Additionally, these models are capable of tackling complex issues such as extracting and calculating digits from document images. The definition of a multimodal large language model is also quite simple. Essentially, it is an AI architecture that can simultaneously process and integrate multiple sensory data, such as text, images, and audio, to produce complex outputs. Multimodal large language models are generally composed of three main components. The first part is the image encoder, which transforms an images into visual tokens. The second part is the text encoder, which can utilize pre-trained large language models such as GPT 3.5. So this text encoder is responsible for translating and understanding natural language inputs. The third part is the middle layer, which converts the visual tokens into language tokens that the text encoder can understand. In this way, multimodal large language models can comprehend and respond to the image inputs effectively. So unlike the industry, universities often lack the extensive data and resources needed to scale performance. Therefore, our main focus is to identify key technologies that can enhance the performance of large language models. After reviewing recent papers, we identified 5 main technologies: cross-modal consistency, efficient vision language fusion, visual thinking chain, fine-tuning with high-quality data, and higher resolution. Among them, generating high-quality data receive a majority of focus. Most methods published in top-tier conferences focusing on using API, such as GPT-4V or Gemini Pro, or general approaches to automatically generate data for instruction fine-tuning. Other methods emphasize increasing resolution quality. Starting with models like Lava, we can see an increasing trend toward enhancing resolution, with some models now achieving resolution as high as 4,000. Now let's move back to the background we proposed the Monkey. We conducted numerous literature reviews and found that most previous works focus on increasing resolution and refining training data to improve the final performance. For example, the original Lava could only support resolutions of 224, and Lava 1.5 increased the supported resolution by adopting a better vision encoder, such as a pre-trained clip model, which supports 336 resolution. However, this was not sufficient. Qianwen used a curriculum strategy and interpolation position embedding method to enable the training of the vision encoder with 1.5 billion data, effectively improved the resolution support to 448. Despite these improvements, there was still limitation due to the high cost of the training resources. Another motivation is the quality of the original training data for multimodal large language models, which often relies on data sourced from the internet. The original image test pairs, such as those from the CC3M datasets, often have simplistic labels like the bedroom stock cottage can sleep people, which do not fully leverage the potential of large multimodal models, which supports high resolution. To address these issues, we adopted a simple yet effective method. Instead of increasing the resolution support of the vision encoder directly, which is very costly, we divided each image into multiple patches, each with a resolution of 448. We then focus on integrating all patches into one overall image by learning the connections between different patches. Recent work, such as InternWheel 1.5, demonstrated that for various datasets, a sufficient number of 448 patches could achieve better results, which further demonstrate it is truly useful to increase the resolution by this low-cost manner. Another motivation is the inadequate representation of data in previous large multimodal models. For example, the original annotation for an image like this might simply state like the future world, selling and chandelier, missing detailed information like the presence of the flowers on the desk. To address this issue, we propose a multi-level detailed description generation method. We use existing lib2 to generate an overall description of the image. Additionally, we employ powerful local object detection method to generate descriptions for specific local objects. We also use the segment anything model to generate descriptions for semantic objects that do not have a fixed shape. By combining all these descriptions into a model like ChatGPT, we can generate comprehensive and detailed captions for images. So as demonstrated on the right, the detailed generated captions might state, this is a formal dining room with a stone feature wall. The room has wooden furniture, including chairs, tables, and cabinets. And there is a budget of flowers on one of the tables and a chandelier hanging from the ceiling. We found that most generated results are accurate, and some even surpass human-level description in details and accuracy. We have generated description for 400,000 images and made them open source. The majority of these descriptions are highly accurate and significantly enhance the quality of the data used in large multimodal models. We conducted numerous experiments focused on image captioning and QA tasks. Our model outperformed Lava 1.5 and other powerful large multimodal models at that time, demonstrating its superior capability in generating accurate and detailed image captions. We also demonstrated the effectiveness of our method in text-centric visual question answering tasks. Using our method, we achieved significant improvements in performance for roles requiring higher resolutions. For example, on the default dataset, our methods saw marked enhancement in accuracies and detail compared to previous models. We also conducted several ablation studies and found that our method achieves better results with increased resolution. So one question that arises is why we only increase the resolution to 896 times 1344. This is due to the limitation of the transformers architecture. The maximum sequence length supported for training large language models at that time was 2048 tokens. Given that each patch contains 255 tokens, we can divide an image into a maximum of 6 patches while leaving space for the generated outputs. This is necessary because the model is autoregressive, producing each token sequentially. Additionally, our experiments validated the effectiveness of the detailed data annotations. We found that our generative data consistently improves performance across various benchmarks, demonstrating the robustness. So to sum up, Monkey has received the honor of being highlighted at CVPR 2024. Our model has also achieved outstanding performance in the Open Campus Leaderboard, ranking as the best open source large multimodal model in January. This leaderboard is also recognized by Meta AI. After we released Monkey, we were surprised by its performance across various scenarios. For instance, Monkey generated some promising results for remote sensing images, medical images, and architectural images. And these results lead us to consider the potential for Monkey to be applied in real-world applications. So initially, we considered whether we could enhance Monkey's capabilities for AI-related applications, particularly making it more useful for test-related tasks. Let's briefly introduce the background of the test understanding. Test understanding serves as the underlying technical support for various business applications. Comprehending tests within images holds significant application potential. Many corporations have dedicated departments focused on tests and image analysis. So according to some statistics, the wholesale OCR market is valued at approximately USD $13.3 billion. The Ministry of Industry and Information Technology has also advocated for the strong development of intelligent products, such as AI-based intelligent equipment. Large multimodal models are key components of these intelligent products, offering capabilities such as financial statement processing, intelligent PDF analysis, element extraction, and chain analysis. And these tasks have clear and practical applications. So before we devise a new test-based large multimodal model, we must ask ourselves, is it necessary? The answer is certainly yes. For all the tasks, such as receive recognition, building small models that perform well on test sets has been quite effective. However, if a user tests a photo of a receipt themselves, these small models may not generate well to the user captured images. In contrast, the large multimodal models we see today can handle most unseen circumstances with remarkable accuracy, and their powerful generalization ability motivate us to pursue these lines of research. So similarly, numerous literature reviews on test-based large multimodal models reveal three main paradigms for image resolution enhancement. The first category use high-resolution models, such as LLaVA, along with extensive test-based instruction tuning data to improve performance. However, these models can only support lower resolution, such as 336 or 448. The second type of method, like Eureader, employs a crop-based approach to increase resolution. The third method, such as Stockpedia, enhances resolution by changing the frequency domain. Although this effectively enlarges the resolution, it requires additional computational resources for retraining, significantly increasing the training cost. For our method, we adopt and build upon the second type, crop-based methods. However, a major issue with crop-based methods is that they can disrupt the consistency between different patches. And this issue is particularly noticeable in the case of the documents, where text is written from top to bottom and from left to right. So if we crop the images, much of the text may be significantly altered or broken up. For example, the word backup might be split into two separate words, back and up. To address this issue, we have implemented techniques to maintain the consistencies and integrities of the text across different patches, ensuring that the crop sections are accurately reconstructed and readable. We bring the ideas of cycle shifting from the swing transformer. By slightly moving the patches, we can capture neighboring information within each window. This slight movement effectively gathers the most useful information for the crop region. So we design this mechanism into the attention layer and place this layer after each VIT, which is from the original vision transformer encoding layer. So these approaches ensures that the consistency and integrity of the text are maintained, and the most relevant information is captured for each crop section. The second motivation, as previously mentioned, is the resolution limitation of monkey at 1,344 times 896 due to the sequence length restrictions of transformers. To reduce the total input length of the large language model, we identified redundancies in the image tokens. By calculating the cosine similarities between the image tokens, we found that some tokens are quite similar, such as the 70s and 80s tokens. Furthermore, we observed that as the resolution increases, the redundancies in the image tokens also tend to increase. So what we aim to do is simply set a threshold to filter out those unimportant tokens. So how did we achieve this? We define an important token as one that is not similar to any other tokens, indicating that it contains unique information. These unique tokens are regarded as important. So based on this, we link all the image tokens and set a threshold value to filter out the redundant tokens. As so in the right images, this method effectively reduces the token count, such as this. However, to mitigate any information losses, we also implement a cross-attention mechanism between the plume tokens and the original tokens, and to ensure the essential information is preserved. We also know that most text-based question answering results can be found within the image itself. To enhance the model's attention to image contents and improve the interpretability of its answers, we introduced pre-training tasks related to text positioning. And so in the bottom right of these images, we employ techniques such as reordering text within images and OCR grounding. So these methods have the model to gain the ability to answer questions accurately while generating the desired response. So by focusing on text positioning, we ensure that the model better understands the spatial relations and context within the images, leading to more precise and interpretable answers. And this is the overall framework of TestMonkey. Given an image, we first split and downscale it into multiple patches. After encoding these patches with layers, we apply shifting attention layers to enhance the relationship between different patches. The processed patches then fall into the image resampler module based on Chen-Wen's method. And the output of the token resampler is then merged with the question tokens. All the merged tokens are sent to the large language model to generate the final answers. We also conduct many ablation studies to evaluate the effectiveness of the proposed components, and the most significant results can be seen in this table. For resolutions of 896, the default numbers of token is 1,304. So when we reduce this into 256 tokens, we observe a performance decrease of approximately 3.2%. However, when we reduce it to 512 tokens, the results do not decrease significantly and even show a slight improvement. So for resolutions of 1,344, the default number of token is 2,304. So when we reduce this into 1,024 tokens, the results do not decrease and even improve for many datasets. For example, for the InfoWiki dataset, performance increases from 29.1 to 31.4, and this demonstrates that the token resampler is both important and necessary for optimizing text-based large multimodal models. We also conducted experiments to validate that the location of the text can be effective for certain datasets. Additionally, using points rather than rectangles or polygons can provide expressive cues that enhance the final visual questioning answering results. And this finding further demonstrates the importance of precise text positioning in improving the performance of large multimodal models. The experimental results demonstrated that our method can significantly outperform previous methods, especially in the OCR bench. And this bench is one of the most widely used OCR-related datasets because it consists of 29 OCR tasks. So TestMonkey can also achieve something that the original monkey model cannot. For example, TestMonkey can handle data structuring issue that is given a chart. It can convert it into structured formats. TestMonkey can also convert the tables into structured formats. Additionally, TestMonkey can be fine-tuned with 10,000 to 50,000 images, enabling it to function as a screen assistant or screen reader. And the fine-tuning process only takes about 1 day of training on an NVIDIA 4090. So all resources related to Monkey and TestMonkey, including papers, demos, models, and other materials have been made publicly available at the link. You can access them online. So we welcome any feedbacks of issues reported, as they can help us to improve our methods. So in summary, we have demonstrated that general large multimodal models can be fine-tuned to become effective domain-specific models, such as TestMonkey. TestMonkey has shown strong document understanding capabilities and interpretabilities. It is also worth mentioning that a recent work, Test Square, which reveals that the average results on several test-based data sets are proportional to the increase in structured data used for training. Currently, TestMonkey uses 400,000 training examples. So if we scale up the amount of the training data to, for example, 10 million, the results can significantly improve, potentially reaching performance levels suitable for real-world applications. So it's also worth mentioning that we have constructed one of the most comprehensive test-based evaluation dataset, OCR bench. And this benchmark includes a wide variety of test-related tasks, such as test relation, test recognition, handwritten mathematical expression recognition, synthetic visual question answering, document-oriented tasks, and key information extraction. And we have observed that many leading domestic and international companies, such as well as the large-scale startups, prefer to use these datasets to evaluate their OCR performance. And additionally, we plan to expand the OCR bench to include multilingual scripts such as Swahili and other languages, even including Oracle-born scripts. And we hope these expansions will further enhance the datasets, utilities, and relevance to evaluating the performance of OCR models across a diverse range of languages and scripts. And feel free to contribute on OCR bench. In addition, we have found that existing OCR-related or general large multimodal models still cannot solve all OCR-related tasks. For example, in video test supporting each task, even the most powerful large multimodal models, such as GPT-4V and Gemini Pro, achieve results that are significantly worse than domain-specific models tailored for video test supporting. So this observation, published last month, indicates that domain-specific test-related models are still required. These specialized models require much less training data and have fewer parameters while achieving better performance in their specific domains. Okay, now let's move on to the future work. So this leads to our future plans for constructing Monkey V2. We have observed that knowing where to focus is crucial for large multimodal models. Hallucination is a significant issue in existing large multimodal models. So by guiding the models on where to focus, we can alleviate this issue. Monkey V2 aims to implement strategies that enhance the model's ability to focus on relevant information, thereby reducing hallucinations and improving overall accuracies and reliability. We also found that existing large multimodal models struggle to effectively understand multiple slides or slide videos. This is because it requires the model to comprehend consecutive slides and provides answers by connecting information across pages. So to address this, we developed a new method built upon Monkey that significantly improves performance in this area. Our new method enables the models to better understand and process sequential information, thereby enhancing its ability to handle multi-slide or slide video content effectively. And we also found that existing, especially open source large multimodal models, cannot effectively solve tasks involving long text, such as PDF. Notably, there is no publicly available large-scale, high-quality PDF data sets for this purpose. So to address this gap, we generated over 1 million QA pairs of various types based on multiple data construction rules, even human being annotations. Some of these pairs are carefully curated by multiple cross-source multimodal models. Additionally, we developed a new method that effectively improves performance and inference for PDF question answering tasks by, for example, indexing the relevant information first instead of inputs all the long text into the model. So this improvements ensure that our models can handle the complexities of long text documents and provide better and accurate results. So we have another paper published in CVPR 2024, highlights our findings on developing new methods specifically for tasks. It is effectively to integrate key information extraction and table recognition into a single framework. And but we still believe that for these types of tasks, it is currently unclear if it's necessary to connect large language models to them directly. Here are some future directions that we believe are worth exploring. The first is about resource efficiency. Currently, large multimodal models require substantial resources and a large amount of training data. So developing lightweight designs would be beneficial to make these models more efficient and accessible. And the second is to enhance the vision foundation model. The existing vision foundation model, we all know that are not very powerful enough. So we need to develop more robust and reliable vision foundation model to improve the overall performance. And it would be better to develop a lightweight vision foundation model. The third is about updating the large language model. So current multimodal models cannot be easily updated because they require extensive data and training resources. So enabling these models to support continuous and online learning capabilities would make them more effective for real-world applications. So the future development of large multimodal models may focus on practical applications, ensuring that these models are efficient, powerful, and adaptable for continuous improvement and real-world use. And that's it for my talk. I'm very excited to be living in this era, especially to witness the power of large multimodal models. And I will continue to devote myself to these fields, and I welcome any discussions. Let's work together to bring the benefits of artificial intelligence to the world. Thank you.
Thanks for William's talk. And as some of you have very familiar with Monkey, I think Monkey is a very good multimodality foundation models, and it has 3 main contributions. Monkey has a strong image encoder, and it can deal with high resolution input. And also, Monkey has data contribution. It has released high quality multimodality data, and even with the grounding informations. And the third, the Monkey also take the implementation into consideration, and it has proposed a token compression method to accelerate the inference speed. And since it's midnight in China, so you can, if you have any questions, you can send the email to Yuliang to discuss. And I think for the Monkey, maybe we can discuss 1 or 2 questions, and maybe if you are interested, maybe I can try to answer some questions of Monkey. So do you have any questions? So okay. So you can send the email to Yuliang. So let's move to the next session. Here is the oral talk. So, Simon, you can introduce for the oral. Yeah.
All right. So now we'll have a series of oral talks, for the papers which are accepted in this workshop. So the first one is SILC, Improving Vision Language Pre-Training for Self-distillation. So we have an online presenter who couldn't attend because of the visa restrictions. So Mohammed Farjad Nadeem is going to present.
Hi everyone, let me know if you can see my screen and I can start.
Just wait a second, Farjad, we are just trying to put it up on the screen.
Sure.
Put the Zoom.
Here.
Just put it there.
Oh, I mean to share this link, right?
Yes. Oh, no, he's already shared.
Yeah.
We have to just.
Oh, I see. So.
Yes, Farjad, you can start.
Great. Can everyone see my screen? I will take that as a yes. So hi everyone, I'm Farjad and I'll be presenting Improving Visual Language Pre-Training with Self-distillation. This work was done in collaboration with my amazing collaborators at ETH Zurich and at Google. So a bit of a background on why we're interested in this. So image language contrastive pre-training has taken over as the default backbone in most computer vision tasks. And this is because these models are trained on internet scale image text datasets, which cover a lot more semantics than any of our supervised datasets. So as a consequence, they learn very rich semantics and have excellent open set abilities. However, towards localization in problems like detection and segmentation, people still utilize self-supervised pre-trained backbones. And this is because these backbones utilize a localization prior in their pre-training tasks. So as a consequence, they do better for these tasks. And what we were interested in is, can we combine the two to have one model that can have excellent open set abilities as well as being good at detection, segmentation, and other computation tasks. So this is where SIL comes in. So SIL stands for Self-distillation from Images and Image Language Contrastive Pre-Training. It's a pre-training method where we take an image text dataset, we sample a caption and an image. The caption goes through a text encoder to give you a feature G, and the image goes through your image encoder, a vision transformer, to give you a feature F. You compute their cosine similarity and you apply a batch-wise contrastive loss. So this is what CLIP has done, and we know it is very powerful and learns very strong model. In addition, what we do is we keep an EMA copy of our image encoder, which acts as a teacher. And now we sample multiple local crops and global crops. The local crops go through your image encoder, which is updated with gradient descent. And you project it to a higher dimensional feature space, and you apply sharpening to get a P of the student. Your global crop goes through your teacher, which is the EMA version of your vision transformer, and you project it to a higher dimensional feature space. You apply centering and sharpening, and now you apply self-distillation loss on this representation. So essentially, what we're asking the model to do is to learn how local regions of the image fit into the wider scene. And as a consequence, the model should learn more about the scene than what's just in the caption. And if you have guessed already, this is what the Dino criterion also does. So the clip has been out there for a while, and Dino has been out there for a while. So what did we need to do to make it complementary? Lucky for us, most of the Dino hyperparameters work out of the box, except for warming up the teacher temperature. So Dino warms it up from 0.07 to 0.04. We find that this warming up results in unstable training, but if you just fix it at 0.04, it works quite well. Something that was very important was that since we use multiple views of the image, it's very important that you align all of your global views with the text. Otherwise, we notice that the self-supervised loss diverges. And finally, we noticed that, so normally with EMA, people tend to use a cosine schedule on your teacher momentum. And normally for image text contrasted models, we tend to use the R-squared root scheduler because it has nicer scaling behaviors. But the R-squared root scheduler learns a chunk of your performance towards the end of your training, and your cosine schedule essentially stops learning towards that state. So it's very important that you match the momentum schedule to your learning rate schedule, or you use a constant momentum schedule, and we find that that works quite well. We do baseline comparisons across several clip methods under the same test plan. So for these comparisons, we train all models for 20 billion example scene, where example scene is a metric of how many image text pairs you sample from your dataset. For these comparisons that I will show next, we use a VIT-B16 as the image encoder and a base text transformer for the text solver. We do have larger models. I'll show them later. We have a 256 image size, and we train these models on the English split of the WB dataset with the 16 KB size. So we're not the first one to incorporate self-supervised learning with image text contrastive learning. So we take some of the popular baselines and scale them to the same compute budget. So we take SLIP, which is SimClear plus clip, XClip, which applies a self-distillation from your caption to your image, plus the clip loss, and MaskClip, which has a self-distillation from a mask version of the image, plus the clip loss. So the first observation that we make is that compared to clip, Silk results in consistent improvement on your zero-shot classification metrics, your few-shot classification metrics, and your retrieval metrics. The second observation we make is that Silk results in the superior performance compared to other methods that improve upon clip. And something that was surprising to us is while in their respective works, SLIP, XClip, and MaskClip have a significant improvement over clip, we find that when you actually scale this to larger compute budget and larger training budget, this improvement diminishes. So MaskClip, for example, does improve upon clip, but the improvement is not as strong when you do also scale up your clip loss. We also apply this with the sigmoid version of training image text contrastive model. So SIGLIP basically replaces your softmax-based batch-wise loss with a sigmoid-based loss, and we find that Silk S, which is the SIGLIP version of Silk, has similar conclusions where you get consistent improvement on your classification metrics as well as your retrieval metrics. And finally, we also find a very nice, training trick, which allows you to extract a lot more performance out of your model without significant extra retraining. So normally, when you're training these models, people have noticed that if you use a smaller, cleaner subset, you tend to learn worse models, and you do need a much larger, noisier data set to learn this. But we find that you can actually use a cleaner subset of your data set in a second stage of your training that we call EMA fine-tuning. So once your main model has done converging, what you do is you have a fine-tuning step where you have a cosine scheduler on your teacher momentum. You use a smaller learning rate, and at this stage, you don't apply a warm-up or a weight decay. And then you just fine-tune for 1 billion extra example scene. And we noticed that this results in 1 point improvement on your zero-shot classification metrics and multiple points improvement on your retrieval metrics. And if you've had the pleasure of training clip-like models, this magnitude of improvement at this stage of training usually requires a lot more compute. So this is a nice way to extract a lot more performance out of your model. So far we're looking at global image tasks. So now we look at segmentation. So the first task that we look at is zero-shot segmentation. And a bit of a background is while we do train CLIP specifically for contrastive matching, MassClip found that zero-shot grounding of caption naturally emerges in the values of the last transformer encoder block. So if you think about it, the CLS feature that your VIT is aligning with the text is actually sampled from the values of your last transformer encoder block. So if you pass these values through your layer norm and your feed-forward network and you do a dot product in the text, you essentially get a segmentation for free. We find that this emerges in all pooling variants of the vision transformer, just at different stages. So if you're using max pool or average pool to get the global feature of the image, this emerges in the output token embeddings of the VIT. Or if you're using our attention pooling head, this then emerges in the values of the attention pooling head. And something that we found a bit counterintuitive to most published research, this zero-shot segmentation doesn't get better with explicitly learning an attention between patches and text, which is very expensive to learn. We find that it is actually the cleaner subset fine-tuning which results in superior zero-shot segmentation. So now we compare the zero-shot segmentation performance of Silk compared to CLIP and SIG-CLIP baselines across 5 datasets. And we notice that compared to the equivalent CLIP or the SIG-CLIP model, the Silk models have multiple MIOU points improvement over all 5 datasets. And in fact, the Silk models are even comparative to more specialized zero-shot segmentation baselines, which do include other objectives to learn better segmentation. So the second observation we make is that this clean subset fine-tuning actually unlocks additional performance out of your model. So we see that similar to before, now we have multiple MIU points improvement over all 5 datasets on both the CLIP version and the SIG-CLIP version. And if we look at it qualitatively, we see that the Silk zero-shot segmentation maps are a lot cleaner. So they tend to segment the objects better as well as assign the correct semantics to it compared to the CLIP baseline, which has a very noisy map. And it's very important to know that this segmentation emerges naturally in the model. This has never been trained for segmentation. While 19 MIU on ADE is nice from a research point of view, it's not something practically which we can use downstream. So next what we do is we take this Silk model and we transfer this to multiple downstream dense prediction tasks where we actually train the model for segmentation detection and other tasks. So the first thing that we evaluate on is open vocabulary segmentation. So we take the current state-of-the-art open vocabulary segmentation model, CATSEG, which is also published at CVPI this year, and we just replace the CLIP model with the equivalent Silk model. How CATSEG basically works is you keep your text transformer frozen. Your VIT is mostly kept frozen. You only fine-tune your attention layers, and you learn a decoder on top of this encoder on COCO stuff dataset. And then this is evaluated on 5 unseen datasets with varying vocabularies. As we compare the Silk models to the equivalent CLIP models, we notice that we get a multiple MIU points improvement over all 5 datasets and all 6 bits. And in fact, the large model of Silk is even more powerful to the G model of CLIP for specifically segmentation. If we look at it qualitatively, we see that the improvements are coming from both better mask prediction as well as better class assignment. So we're improving on both the dimensions that are important for semantic segmentation. Next, we touched on semi-supervised segmentation, which is a very data-constrained setting where, for example, for ADE, now you only have 158 labeled examples and the rest of the dataset is unlabeled. And we notice that just replacing CLIP with Silk gives you a multiple MIU points improvement, further validating our hypothesis. We next test on open vocabulary detection, where we take OWL v2 as the object detection backbone, and we just replace CLIP or SIG-CLIP with the equivalent Silk model. And we notice that on both COCO and LVIS, we get multiple points improvement, where the improvement is especially prevalent in the very classes, which are the ones you most care about when you're doing open set object detection. We also evaluate the Silk visual representation with lit decoder. Lit decoder is a benchmark where you freeze your vision transformer and then you learn how to replace a decoder on top to do multitask learning. And we noticed that just replacing CLIP or SIG-CLIP with the equivalent Silk model gives you a decent improvement on both classification, captioning, and question and answering. And we noticed that the improvement on captioning and question and answering, which requires the model to understand local context better, are more significant. We also study how do the teacher and the student differ throughout the training. So once the model has converged, we notice that for the normal VLM task, the model had this teacher and the student have similar performance. But if you look at segmentation, the teacher tends to outperform the student for segmentation. We also plot here the performance of teacher in orange to student in green throughout training. And we notice that for most of the training duration, your teacher is well ahead of your student. But in the end, they converge to a very similar point. except for if you have a scheduler mismatch. So if your momentum schedule mismatches with your learning rate schedule, your teacher can fall behind because the cosine schedule will stop learning towards the end. So it's very important that your momentum schedule matches with your learning rate schedule. So since we're using multiple local and global cross, we do use a lot more compute compared to training an equivalent CLIP model. And on average, Silk training requires 4 times more core hours compared to CLIP training. So a 5 billion duration Silk model would consume the same compute as a 20 billion model, and similarly a 10 billion would consume the compute of a 40 billion model. And when we normalize for compute, we notice that at 5 billion, the Silk model is outperforms CLIP for classification, but is slightly behind on retrieval. But when you train for slightly longer to 10 billion, now the Silk model outperforms CLIP on both classification and retrieval. And further training, CLIP doesn't give you more performance. So CLIP tends to saturate around this performance, and Silk is able to extract a lot more performance out of the same data set. We also scale Silk versus CLIP. And in this experiment, what we do is we train both of these methods until they stop improving. And the criteria we use is that if the model doesn't improve for 20 billion examples in duration, then we stop training. The curve below is the cyclic curve, and the curve above is the Silk curve. And we notice that for throughout your training, Silk is superior to cyclic. And towards the end, cyclic achieves the best performance of 76.7 on B16. And Silk is able to extract a lot more performance from the same data set. So the best Silk B16 model actually gets 77.40 short image net, which is the best performance that we're aware of. We also scaled Silk to larger model sizes and smaller pad sizes. And we noticed that at each model family, Silk is the strongest backbone across all benchmarks. We also, so far, all of our comparisons are done on WebP. And we also, in these comparisons, test on open source image text dataset. So now we take CC3 million, CC12 million, Lion 400 million, and Lion 2 billion. And at each data and compute scale, we see that Silk is the strongest model across the board. And in fact, while we didn't develop our model on Lion 2 billion, it actually outperforms OpenClip by 4 points on zero-shot ImageNet and similarly on retrieval. With this, I conclude my talk. So in this work, we propose the self-distillation from local image crops as a complementary supervision signal for image text and trusted models. We show that Silk models consistently improve performance on tasks that require global and local level image understanding. And we show that Silk models scale better with data and compute. With that, I thank you for your attention, and I welcome any questions.
So any questions for? So maybe I can start with one question for Josh. So how sensitive do you think the SILC framework is to the choice of the teacher model? Did you experiment with any alternate choices there?
We basically tested having a EMA teacher versus not having a EMA teacher, and the EMA is needed for to prevent collapse. We didn't try any other variant.
So my question was more on the different type of would it make sense to use any alternate teacher model, and can it help in terms of helping with the performance?
I see. So that's an interesting question. We haven't tried it, but for example, DynaV2 shows that if your teacher is actually a larger model, your student can learn a lot more. So that would be an interesting experiment, but we have not tried it in our framework. But mainly because our teacher is actually constructed from our students. So then you would need to have a different way to construct your teacher.
Okay, so if there are no other questions, maybe we can move on to the next oral talk.
Okay, thank you, everyone.
Okay, this better? Well, maybe somebody should mute. So what are we trying to achieve here? The goal is to train models that are robust to visual domain shifts. And visual domain shifts reflect the challenge of the same set of object classes having pretty much different visual appearances in different data sets or between training and testing conditions. And we want to have models that are robust to this visual domain shifts, but without requiring labels for all these domains. Right. Is it going to the next? Let's do it like this. Okay, so here you see an example of one object class with having very much different visual appearances. Okay, we will be using or looking into vision foundation models and unsupervised domain adaptation. But before we go into the details, these bare necessities, I will first tell you a little bit about our motivation. Because what we observe that in industry, there are many tasks that could potentially be automated via computer vision. But in order to do so, you need to have a sufficiently large and high quality labeled data set. And often in many industry applications, think of robotics, the cost of obtaining such a high quality labeled data set is still too high compared to the benefits. So what we aim to do is to improve the scalability of computer vision by making sure that we can train higher quality models with less labeled data or with less real labeled data, because we will also be leveraging synthetic data. Okay, the focus of our research is on unsupervised domain adaptation and vision foundation models. And we are very much interested to know how complementary are these technologies. So far, to the best of our knowledge, in UDA research, people have not been using the benefits of vision foundation models. So our contribution is this combination and mainly exploring the complementarities and the benefits of combining these two technologies. That brings us to the details on these methods. Let's start with unsupervised domain adaptation. In unsupervised domain adaptation, you typically have a source data set that has labels. In this case, it is a synthetic data set. And the goal is to train a model that performs well on a target data set for which we don't have labels. Now, if we look here on the right side, this is our representation space with regular ImageNet 1K pre-training, so not a vision foundation model. Then we can put in there our source representations, which have labels. And we can also put in our target representations, which don't have labels. And then these are two domains or two data sets that relate to the same kind of application, same kind of scenes, same kind of objects, but there is a visual, let's say, domain shift between these two data sets / domains. If we would now do no UDA and we perform regular supervised learning, then we would train a classifier, and that classifier, shown here by the thick black line, would be able to classify properly all the representations that are inside, and it would also be able to kind of interpolate the gaps of the data set. So inside the data, it can do that, but it's rather limited in kind of extrapolating beyond the distribution of the data set on which it was trained. So to this near or out of distribution data. So this classifier would be able to already classify correctly a part of the target, but certainly not the entire target. So then what does unsupervised domain adaptation try to do? It is to pull these target representations that don't have labels towards the source representations. Let's see, what's that? Yeah. And by doing so, the UDA uses the labels of the source to kind of ground the classifier so that it doesn't move, and it uses a combination of techniques, most importantly, self-training via pseudo-labels to pull the target representations towards the source, and by therefore, and in that way, it can classify correctly a larger part of the target. Okay, that is interesting, but so far no vision foundation model is being used. Let's have a look how vision foundation models relate to this. Well, let's start first with the same representation space, no image, no vision foundation model pre-training, but we have now this tremendous large data set of images on the internet that we can use for self-supervised pre-training. Now, of course, vision foundation models don't necessarily focus on a specific target, but for our research, we include it here. Now, when we go to when we do vision foundation model pre-training, we basically have this the entire representation space. We have a very large collection of images, so we can basically use those images to better structure this representation space. At least that is our hypothesis. And by being able to better structure that representation space, automatically the source and the target representations will already be closer together, just because of that massive pre-training on unlabeled data. This will already help a regular classifier trained on the source labels to perform better on the target labels. But we also hypothesize that there is a second effect, and that is that by using a vision foundation model, the classifier is also better able to extrapolate or to classify near and out of distribution representations. So it's better able to generalize beyond the labels. Now, if you look at this picture, you would think, yeah, why do we still need unsupervised domain adaptation? But this will already work. And this was also then kind of the motivation for us to dig deeper and do a set of experiments. That brings us to the research question. The research question is, okay, to what extent are these two technologies complementary to each other? Can they be combined? And what are the benefits of these models for in-target and out-of-target generalization? That brings us to the research methodology. Okay, we're going to take, let's say, state-of-the-art UDA methods, state-of-the-art visual foundation models, try to combine them, and then do a series of experiments. These are kind of typical UDA type of experiments, where we have a labeled source domain, in this case, GTA5, which is synthetic. We have an unlabeled real target domain, which is cityscapes, but we also include an unseen domain. That also has a domain shift, but that data has never been seen during UDA. So that allows us to assess better this out of distribution or near distribution generalization. In order to, let's say, properly quantify or get insights into our results, it's also important to have a baseline. And the baseline for all our experiments is basically regular supervised training using the labels, and then assessing the capability of that model for the two other targets. Of course, we have our UDA approach, and we have also an oracle. For the oracle, we use the labels that we have in these experiments for the two targets, use regular supervised training to get a model. And these baselines and oracles basically provide a lower and an upper bound for the UDA performance and allows us to better assess their performances. Yes, okay, then let's look at the results. This is the experiment where we go from GTA5 synthetic source with labels to unlabeled cityscape dataset from UDA. We also assess the performance on this unseen domain well-2. Over here, a small selection of all the experiments that we did in the paper. There's much more, but we take a state-of-the-art UDA method, MIC, that does not use a vision foundation model. It's pre-trained on ImageNet 1K. And we take our combinations of vision foundation models in UDA, and we use the vision foundation model Dino V2, because in prior experiments we saw that that was optimal for these kinds of semantic segmentation tasks. We have two model sizes, and we assess the performance for in-target and out-of-target. Let's have a look at the baseline performance. So this is regular supervised learning, no UDA yet. Then you already see a significant benefit in using the vision foundation models. So that comes back to that picture that I saw, that by using this vision foundation model pre-training, these two distributions of the two domains are already closer together. There's more overlap, so it can already classify better a larger part of the targets. Okay, we also have the oracle, and then we have the UDA approaches. Now, what we can observe over here is that UDA still has added value on top of a vision foundation model. So that picture that I showed you before, where this vision foundation model basically solved everything, that was not correct. Luckily for all the UDA researchers maybe here, UDA is still of added value. But maybe in this experiment, the same does not hold for the vision foundation model. Well, because the added benefit of the vision foundation model for the same model size, yeah, is, of course, it's there, it's significant, but it's not huge, it's not shocking. I'll come back to some other benefits of the vision foundation model later. But first, let's have a look to the out of target performance, so to data that has never been seen during UDA. Okay. We add our baselines, so we again see a significant improvement in just the generalization capabilities without doing UDA. We add the oracle, we add the UDA method, and now out of target, we see a significant delta, positive delta, by using the vision foundation model. So this does not use vision foundation model, and these two do. But then, when you look out of target, the benefit of doing UDA, that is going from here to here, that then has become marginal. It's not surprising because UDA only focuses on the target and not on that unseen domain. But from this, at least we can conclude that vision foundation models and UDA are complementary. UDA mainly helps for the in-target performance, and the vision foundation model mainly helps for the out-of-target performance. When you now think about it, it's also quite logical. In the paper, we have also reel-to-reel experiments, much more, but over here, I only want to show you one more set of experiments. So here we are going to scale up the model size of the vision foundation model. So we start on the top here with MIC, which is not a vision foundation model. Then we have here the in-target mean IOU for regular pre-training and vision foundation model pre-training. So this is not a vision foundation model, so it doesn't have those numbers. And we also measure the speed up, and this is our baseline. So there's no speed up, it's the baseline. Okay, let's go to the model sizes. So this is the small model size. We see, of course, a significant speed up, but we're also not matching the performance of the non-UDA approach because it also has less parameters. Then we go to the base. The base has the same number of parameters. It is a bit better than the MIC method, but it's also much faster. And that is interesting because the VIT is a plain VIT, single resolution, and we're also not using the multi-resolution decoders that MIC is using. Now, for MIC, it's crucial to obtain that top performance by using these multi-resolution decoders, but they're also very computational expensive. Our plain VIT so far is not compatible with these high-resolution, multi-resolution decoders. It also doesn't need them because it already obtains even slightly better performance. But by not requiring high-resolution decoding, it's also way faster. Even so, if we now go to the large model, which has way more parameters, we get a bigger delta, 79 mean IOU, it's still 3 times faster. So that's interesting. Another important observation is that by using the foundation model pre-training, we don't see this plateauing effect. Over here, we use regular pre-training, and you see that scaling of the model size does not help in UDA performance. Whereas with foundation model pre-training, we do see that it keeps on scaling. This is maybe important for the future, where we go into larger and larger and larger model sizes. Okay, so by using vision foundation models, we scale better, and we are also more efficient so far. Okay, this is a workshop, and this is ongoing research. So I also want to give you a bit of a glimpse in what we are currently doing and what we will be doing next. Let's first have a look at the conclusions. So VFMs and UDA are complementary. The UDA on top of the VFM really still helps for the in-target performance under large domain shifts. This was from synthetic to real. In the paper, that's also from real to real, and they see a bit less benefit of doing UDA on top of the VFM. The VFM really helps UDA to also have proper out-of-distribution generalization to unseen data. And it's also 8 times faster because we don't necessarily require this high resolution / multi-resolution decoding. Okay, what are we currently working on? We are also scaling up the data set size. So the synthetic data and the unlabeled data. And then we see the same effect when we are not using a vision foundation model. The UDA cannot take, let's say, proper cannot properly use that increase in data. But with the vision foundation model, it can use that data. And we are able to go above 80% mean IOU by only training on synthetic data and then testing it on real cityscapes data. And when you would use cityscapes labels, you get an 83% mean IOU point performance. And we are already very close to that upper bound by only using synthetic data. And that is made possible because these vision foundation models scale to larger model sizes and are better able to use more data during UDA. At the same time, we also know that this multi-resolution information, either using the encoder or decoder, helps UDA a lot, approximately +5 percentage points. We cannot use that multi-resolution information because we have a plain VIT, and so far we have not been able to make it compatible with multi-resolution decoders. But we also then don't really know if it's needed. Maybe this Dino V2 in its pre-training already sees images with different resolutions, so it has already learned with the plain VIT to handle multi-resolution information. We don't know, but we find it an interesting direction to explore this further. If we can really maybe close this gap from 80 to 83 even more by using a bit of multi-resolution information, either in the decoder or somewhere in between the encoder and the decoder. And with that, I thank you for your attention and happy to answer questions.
Any questions for our speaker?
Oh. Well, if you can think of some, then we will be at the poster with more details.
Yeah.
Okay.
Maybe I can ask one question. So, any specific reason why you are only working with Dino V2, or like was there any comparison?
We did definitely a comparison. It's also in the paper, and we even did a more extended comparison. And we also have a poster on that next to this poster, where we took really a lot of vision foundation models and assessed them for the task of semantic segmentation. And then we specifically see that for data sets that require, let's say, a lot of detail, such as cityscapes, but also where you have the same object appearing very large, but also very small, for instance, a car nearby, a car in the distance. In those kinds of situations, Dino V2 is really outperforming the other vision foundation models. So that's why we're also using it in these sets of experiments. Yeah.
Thank you.
Thanks.
The next thing, yeah.
Could you go back to the last slide?
This one? Yeah.
Can you explain how you were able to, using the Dino V2 on fully unlabeled data, you got an IOU of 80%. Did you have to train it on label examples as well?
So it's UDA. So we have labeled a labeled source domain, but that's only synthetic data. So that's a combination, I believe, of GTA5, Cynthia, and another one. So it's only synthetic data that we have labels of, and then we domain transfer it to this real data set, cityscapes, using the UDA techniques and the vision foundation model. And then we achieve this. So for sure, there are labels being used of the source.
For the 80%, no.
Yeah. Yeah, well, for the source always has labels, but it's synthetic data, right? So it's not the real cityscapes data. Yeah. Yeah.
All right, so if there are questions, let's thank the speaker again.
Okay, thanks. Okay, who's next?
Let's move to the third forum.
All right. photo. Okay.
Great. So we have the last oral talk from Fan, who is going to present his work on towards a diffusion-based generalist model for dense prediction tasks.
Thank you very much. So hello, everyone. My name is Fan. So today I'm going to present our project on toward a diffusion-based generalist for dense vision tasks. So this is a joint work between Max Planck Institute for Informatics and Google. So our co-authors are Yongqing, Xiaohua, Alexander, Farjad, Bent, and Federico. All right, so let me start with the motivation first. So, recently you have seen that autoregressive transformer has been a prominent unified approach for many kinds of NLP tasks, right? You have this sequence in, sequence out format to for like all kinds of NLP tasks. But in contrast, the computer vision models still have a lot of complex task-specific designs. For example, semantic segmentation have this kind of per pixel class label, and for object detection, you have this bounding box, right? And therefore, in this work, we explore a diffusion-based vision generalist, where we try to unify different types of vision tasks as a conditional image generation, and then repurpose a pre-trained diffusion model for it. So as you can see from the this figure here, right, at its core, we have this one single diffusion generalist model, and then given some input image and the corresponding text prompt specifying what kind of task should be performed now. And then the model will give you the corresponding output, and then you decode it back into the original output format to do the evaluation. I'll explain this RGB image part later. And secondly, in this paper, we also analyze the important design choices for designing such kind of diffusion-based generalists. I'll also talk about like in the ablation study. All right, so before we dive into the detail, a little bit about related work. So you probably already heard a lot of work around this topic, unified vision models. And here we differentiate between two branches. One is unified architecture, but task-specific parameters. Here you have some segmentation-only model and the segmentation plus other tasks. So for example, this UVim and decoder, they fall into this category. Basically, they have this kind of unified architecture for many different kind of vision tasks. But then, like when you talk about specific task, you still need to train like one model to do it, and the different model do not really share the parameters. And therefore, like in this project, we're more interested in a unified architecture, but only have one single set of parameters. And so this highlighted branch is like the track we're competing with. We're aiming to build a single model to solve many vision tasks at the same time. All right. So coming to the method section, as I mentioned earlier, right, we unify different types of vision tasks as conditional image generation. Therefore, the first question to ask is how to reformulate the output space of different vision tasks into RGB image. And that is this data reformation part. And then once you can get this done, then you could just take some standard diffusion model pipeline to solve it. And in this second part, we're interested in the training recipe for diffusion-based generalists. All right, so let me start with the data reformation part. So let's take semantic segmentation as one example, right? To achieve this, like given this kind of input image, right? To achieve this kind of RGB target image, we need to first define some injective class 2 color mapping, right? In this example here, we define that bus should take this color, which is greenish, and the sky should take this brownish color, and road should take this bluish color, right? And then given this kind of class 2 color mapping and the ground truth mask, then you could construct such kind of a target image in the RGB space, right? And then you do this for basically all samples and also all data sets. And after this, then you will have like a data set in a new format where the input is just the like original image and the corresponding text prompt, and the target is also RGB image, right? Once you have that, then you could just deploy a diffusion model to solve it immediately. Right. Therefore, in terms of the method part, it's pretty much the standard diffusion model. But here, I also want to highlight a few points. First one is that we perform diffusion in a pixel space to avoid some sort of a quantization error for like during the decoding part. So very quick recap of the difference between pixel diffusion and latent diffusion. So for pixel diffusion, you directly like apply this diffusion process in the pixel space on the original image. In the latent diffusion, you first turn through some VE or VQ-GAN like model to map the image into the latent space. And then in this latent space, you perform this diffusion. This is like much more efficient. But then there's some issue, like when you decode from this VQA or VQAE like decoding process. And I'll talk about this more like in the ablation part. So basically here we found that latent space diffusion has much worse performance than the pixel space diffusion. And therefore, that's the choice of our model. We use the pixel space diffusion. And secondly, we found it's very beneficial to not directly condition on the original image, but condition on some multi-scale feature pyramid extracted from some image encoder. That is this middle part here. We applied it on the original image. You extract the feature and then use this as the image conditioning, right? And of course, we have this text conditioning to specify which task is performed now. Right. And last but not least, we also find that using some text-to-image generation pre-training is also very beneficial for the final performance. Right. So overall, this method is quite simple. We unify like a different kind of vision task as conditional image generation, and then use a diffusion model to solve it. So let's first take a look at this pixel diffusion versus latent diffusion, which I mentioned earlier. So the problem of using a latent diffusion model is that it has this very bad quantization issue, where even though your UNet can give you very accurate output like this latent vector, but when you use the VQ-GAN decoder to generate like kind of reconstruct the original RGB image, then this reconstruction is not very accurate and then gives like different pixel values. The performance will also be bad. So here is one example of this failure case of the latent diffusion model. So on the left-hand side, you have the input image, right? And then we just ask the model, now you should perform a semantic segmentation task, right? And then give you this kind of RGB image. So this RGB image is actually from the latent feature of the UNet and then processed by the VQ-GAN decoder, right? So if you take a look at this red box, inside here, you see the same colored pixels, but it actually has 4 different pixel values. And therefore, when you map it back to the original class space, it is they are actually mapped into 4 different types of classes. And therefore, if you compute the MILU, the performance is going to be very bad. So that's why you see here, right, on semantic segmentation and panoptic segmentation, if you use latent diffusion model on 8020K, COCO, so these are the performance. But if you use the pixel space diffusion, then these are the performance. You see the gap is like really significant. So here we conclude that the latent diffusion suffers from this quantization issue, while the pixel diffusion can achieve a very good performance. So yes, apart from this, as I mentioned earlier, we're also interested in other design choices in such a diffusion-based generalist. As mentioned earlier, 3 points, right? First of all, diffusion model can greatly outperform the non-diffusion model, on some panoptic segmentation where the global understanding of the object is needed, right? So if you compare the first row and the second row, right? That is ours versus non-diffusion. You see the performance gain like on the 8020K and the COCO. And secondly, text-to-image generation pre-training is also very important. You could very well just, because I mentioned earlier, it's a very simple method. You could just train the diffusion model from scratch, right? Because it's also not image generation, but image generation helps. It's like serves as a very good initialization. So compared to train from scratch, like using a stable diffusion pre-train checkpoint, it gives like a better performance. And lastly, if you direct concat on the raw image, the performance is also not very good. You need to condition on the image features that is extracted by a powerful kind of encoder. All right, and then come to the comparison with the state of art. So here, as mentioned earlier, we evaluate on like dense prediction tasks. So here we evaluate our method on 6 different tasks. So depth estimation, semantic segmentation, panoptic segmentation, and 3 types of image restoration tasks, that is denoising, deraining, and image enhancement. I'll show you some visualization later. And you can see the comparison between our method and the previous method here. So we can see that our method can actually achieve very competitive performance while using a much smaller target resolution. So for example, Painter, which was a previous state of art method, for this vision generalist, used like a 448 by 448 target image resolution and achieve this performance. And our method using a 128 target resolution can also achieve like competitive performance. And for this dense prediction task, the target resolution really matters, because if you shrink down the image resolution, a lot of small objects, they're just simply lost in the image, right? And a fairer comparison would be, we also downsample the Painter's target resolution, retrain it again, and achieve this performance here. And then you can see that at the same target resolution, we outperform Painter with by like a very large margin here. Basically, also showing the promise of this method. And the reason that we didn't really scale up our target resolution is because we actually moved from the latent space to the pixel space, right? If you remember, the original motivation of using this latent diffusion is for the efficiency, right? If you move it back to the pixel space, it's going to be very expensive. But we have no choice. We have to use the pixel space diffusion to avoid this quantization issue that I mentioned earlier. And therefore, increase the targeted resolution cost a lot of memory, and we simply couldn't do that at this time. But in the future, we're also considering like other techniques to increase this resolution, and hopefully can close the gap with the state of art. Right, and lastly, I want to show you some nice visualization. So here I show you 3 tasks: semantic segmentation, panoptic segmentation, and depth estimation. On the left-hand side, you have the original image, and the middle, the second column here is the ground truth RGB image. That is like constructed from the ground truth label and this kind of class to color mapping stuff. And here we have our model's output, right? And this is the prediction after the post-processing. And as you can see here, right, you don't see this kind of a nasty region again, because as mentioned earlier, moving to the pixel space really solves this problem. And also you see this kind of a painting, right? The edge is quite sharp. Yes, and then the last one, the 3 types of image restoration tasks on denoising, deraining, and light enhancement. And our model does pretty well. And you see this kind of artifacts, because these images are of a very small resolution. If you can see from this label here, it's 64 by 64. So we did this visualization on the small image. That's why it looks a little bit blurred. All right, so with that, I conclude my presentation. Thank you very much for your attention. If you have any questions. Yes, please.
To clarify on
Yes, exactly. So this is the target RGB image, right? We do the noising process and then put it directly into the UNet. Give me some sweet spot between. Actually, as you can see from this experiment here, the latent diffusion model performs actually pretty bad on these two tasks. So we actually didn't really use it in the end. We directly moved to the pixel space. And by compromise, I don't really understand how would you like find a middle ground between latent space and pixel space? Do you have any? Okay, I see. Actually, yes, actually, I guess the problem of this latent diffusion, this quantization error is because the VQ GAN decoder is not really involved in the training, right? So in the training, you only have this denoising UNet part, right? So we actually checked if just on the UNet part, the output is really accurate. It's what you really want. But the decoding process of this VQ GAN is problematic. The reconstruction there is not very accurate. So we also try to basically fine tune the VQ GAN on these kind of target images, but then it also lose performance in encoding the photorealistic images. And then there's always this trade-off of whether you wanna your VQ GAN be more performant on this part or on this part. And it's really hard to find a sweet spot. So we just abandoned in the end, directly moved to the pixel space and find it's a very good solution. But yes, you're right. The training cost is very large. Yes, please. Yeah. Yeah, actually, that's also what we're doing now for even for this experiment. So you have, let's say for 80/20K, you have 150 classes. You evenly distribute these classes, or you evenly sample like 150 classes from the RGB cube, right, to maximize the kind of usage of the space. But then the problem of this reconstruction is so bad, it can give you like completely off pixel values, but then still looks visually similar color. And then this will be like if you do this the nearest neighbor to map it into some anchor pixel some anchor pixel value and shows the corresponding class. It is indeed this bad. And we also thought about maybe add like some more learnable parameter or another learnable layer to map to do this mapping rather than do nearest neighbor. But then the problem is that if you're in this RGB space, there's no semantic. So there's no semantic correspondence between the class and RGB value. For example, if you see like from the previous example here, right, we say bus should be this color, right? It's actually quite random. It doesn't encode any semantic information. Therefore, learning this would be also not really ideal. Therefore, it's, yeah, we couldn't really find a good solution than just move it back to the pixel space. Yes. I see. But also the dimension is like too small. It's only 3 dimension, right? But the text embedding is like really huge. I guess, yeah, it's going to be very difficult, I think. Yeah, but thanks for the question.
I think we have an online question.
Oh, sure.
You can see. Can we use any task that cannot be expressed in the pixel space? For example, multiple detection or the pose estimation.
Okay, yeah. Let me repeat this question. Can we use any task that cannot be expressed in pixel space, for example, bounding box detection or pose estimation? That's a very good question. Actually, this idea of doing this data reformation in the RGB space was inspired by this painter work here, They also did some experiments in terms of this localization task, right? And the way they do it, so they perform this key point detection on the human body. The way they do it is that you take one key point, let's say head, right? You have a XY coordinate, and then you just draw a heat map around this key point, right? You just draw a heat map around it, and you make it into RGB. And then you ask your model to generate these kind of images at test time. Once you get the image, then you just say that the center of this heat map would be is the location of this key point. So in this way, you can also transform this kind of localization task into an RGB space. We also did some initial experiments on it, and it works, but we didn't really include it like here. All right, more questions?
All right, so if there are no other questions, let's thank the speaker.
Thank you.
So we have a poster section break, and we will be back in welcome back. So let us welcome Professor Li Yuan to give the keynote talk. Professor Li Yuan is an assistant professor at Peking University, and he has been selected as the National Outstanding Overseas Student Award and Forbes Asia 13 under 13. His research primarily focused on multimodality in machine learning. Li Yuan, you can share your screen.
Okay. You may stop your, okay. Can you see my screen? Okay, let's start. Hello, everyone. I'm very happy to introduce our open source plan, the video generation open source plan, and our current progress and the challenge. I'm Li Yuan from Shenzhen Graduate School of Peking University, and we released this project around 3 months ago. And before I introduce our framework, our research, our open source plan, I would like to show some generation results of our current version. So the red one is cookie vlogging itself, but you can see the motion is not very clear. And this one is a 3D animation of a small rolled fluffy creature with big expressed eyes. The current generation result is not comparable with the Sora or the Clean, some such model, but we believe that it's the next version may be much better than current version, and also we are open source. You can download our model pre-trained parameters and a more longer video. This is a draw camera circles around a beautiful historic church building. As you can see, when the camera changing, the building shape is also cannot keep. That's the consistent problem, and we will improve in the next version. And this is a liquid metal. Oh, you have seen the cookie before. This is a 3D animation. The road view. Okay, the closing of the man is changing. Oh, this one, I like this one. This is a real view of the Centaurian
during the blue hour. This is a cat wearing sunglasses and working as a lifeguard at a pool. But if you can see his hand, it's not like a lifeguard. I really like this. It's also a church and the barbecue with fire. You can try our model on the Hugging Face, and we also released the parameters and even all the training data. So first of all, I would like to introduce the motivation of our open Sora plan. So our motivation is quite simple. We would like to reproducing a mini Sora. Why we want to do that? If we look back to the large language model, we know that the ChatGPT was announced in around 1.5 years ago, which can be accessed by anyone, but it's not open source. In that time, we know if we want to do some research, the community doesn't have an open source model, and also the industry also needs some such model to do applications. We know after around 3 months, the Meta AI released the first version of the Llama, which is of course not comparable with ChatGPT at the beginning in performance, but at least we have an open source model, and we all know the story behind Llama, including Llama 2, and this year the Llama 3 getting better and better, and we can do research based on Llama. For example, the Lava is based, the many multimodal framework is based on the Llama. So, but for text to video, the video generation model, we still need the big company to release a model for us. So what I want to do is just we want to do a social experiment that can we open source a text to video model by using the power of the open source community. So three months ago, we announced this plan, and our framework including 3 parts. The first part is a video autoencoder, is the pink part. The second part is a diffusion transformer, as you know, the diffusion process and the denoise processing. And the third part is a condition module. This is a text condition encoder. In our work, we use T5, the text encoder, but you can also use other open source large language model as a text encoder. So after we released this plan in X and GitHub, the community is actually very active, and we're feeling the passion of the community. You can see very quickly we get the GitHub trending #1, and also in the first week, our repo, the open source community has also very high participation. In the first week, I remember we're integrating more than 30 pull requests from the creator, from the other creator, and we also update our model and codes more than 200 times within 1 week. So let's look at the details of our plan, our open source plan framework. So the first part, as I mentioned, is the 3D video VAE, which is including a video encoder and a video decoder. It's very similar to the latent diffusion model, but we don't use image encoder. We train a video encoder and a video decoder. A video VAE is a 3D video VAE, which can compress the original video to the no dimension latent space, and then our video decoder will reconstruct the video from the latent feature. But of course, in the second part, we do the diffusion process based on the latent features. So the reasons to do compression is very simple. First, the original video is too large, and also optimization doing in the latent space is more friendly. And but
if we want to do the 3D compression, we also need compress on the time dimension. So we get the temporary and the spatial patches. We do the diffusion, the generation on the latent space. After that, we decode to the video space from the temporary and the spatial patches. We know that the most important thing for the 3D VAE is keep the high TSNR reconstruction results, but also with high compression. So what's our structure? The structure is also quite simple but effective. Our last version, the encoder including 4 3D blocks. In each block has 2 residual blocks, 3D residual block, and a spatial downsampling and a temporary downsampling. But in our current version, we have the encoder. We change the first 2 3D block, 3D block to 2D blocks. This can be more compatible to the much duration video, and also be more dynamic to the input of image and both image and the video input. So our framework can also do the image compression and the reconstruction. We use for the 3D block, we use the Castle Conv 3D, which is converting the Conv 2D to Castle Conv 3D, which can enable joint training of the image and the video data. And also Castle Conv 3D applying a spatial treatment to the first frame, as it does not have access to the subsequent frames. On the other hand, there are 2 common methods to expand the Conv 2D to Conv 3D. The average initial and the center initialization. But we found that this 2 initialization is not good, and we empirically employ a specific initialization method, the tile initialization. This initialization method ensures that without any training, the model is capable of directly reconstructing images and even videos. We know that we believe that the 3D VAE, the compression is crucial for the Sora-like framework, because we always know that the OpenAI always claims that the compression as intelligence. So based on such believing, so we design and train our 3D VAE, get a good results. So if we can say that we currently we can compress 1 minute 1080p video to the latent space, and the GPU memory is less than 8 G. So one single GPU can load such long video during training, of course during inference. If we load the 30-second and 720p videos, the byte size can be set as 4. So that's very important, because we believe that the stable video diffusion cannot generate non-video. The reason is it always cuts the video to short clips. If you remember, the video length always 16 frames in stable video diffusion. So how can you ensure that the model training on such short video can generate a long video? So, but for Sora-like framework, one of the reasons is that the stable video diffusion uses the image VAE. They didn't compress the video in the temporary dimension, which only compressed the video in the spatial dimension. But for 3D VAE, we compress both spatial and the temporary dimension. And here is a reconstruction results. So you can compare the left and the right. The right one is the reconstruction results. The left one is the original video. You can see the reconstruction result is quite good. So we believe that the reconstruction results of the 3D VAE is the upper bound of the generation results. If your model cannot reconstruction a long video with high resolution, your model cannot generate such long video. So we do quite a lot of work in the 3D VAE. And currently, our causal video VAE, our 3D VAE, achieve more than 200 compression ratio, and the PSNR is larger than 30. Here is a demo for 1 minute, 720p video reconstruction by our 3D VAE. Besides, our model can also reconstruct the image. The left, the right, these two images are reconstructed by our 3D VAE. So you see the reconstruction result is quite good. And the next version, we hope we can improve the compression ratio based on current model. Okay, the second part is the diffusion transformer. So this is not hard to understanding because we all know diffusion model now. But for Sora-like framework, it's changed. It's not use a unit-based diffusion model. It's changed. It's use a diffusion transformer. Also, because this is not image generation, it's video generation. So it will do video denoise and video diffusion and video denoise. So that's basically we need to do 3D diffusion transformer, the 3D attention on the video latent feature. So, but the 3D DIT need more computational cost. We are using in the next version. Currently, we are using the 2D plus 1D diffusion transformer. You can see that here is the original DIT framework. If we want to apply this to video generation, we need change the 2D attention to the 3D attention. But as I said, it's need quite more computational cost. So currently we are using this 2D plus 1D DIT similar with the NATE. So first we adopt the spatial, we adopt the spatial attention, the 2D attention, then it's a temporary attention, then spatial, temporary, the such structure to do the video to do attention on the video latent features. On the other hand, we also trying to explore more structure like the 3D DIT and with the MOE, the mixture of export. We believe that it also can reduce the training and the inference cost. We have explored such structure on the multimodal like the Lava. Our MOE Lava has been verified that the active parameters around 1.8 billion, and it can achieve comparable results, comparable performance with the interval chart 19 billion. And so this structure is also not hard to understanding. We train the MOE Lava by 3 stages. The first stage is the normal training. Is generate the text caption as a Lava. In the second stage, we train this part, the FFN and the self attention, and also the word embedding and the MFP part. Then we copy the weight to the stage 3. Stage 3, we fix the self attention part and split the FFN to different export. So we are also trying to do that on the 3D DIT, which means that after we pre-train our model, we can apply such MOE, the mixture of export structure to the 3D DIT. And also we believe we found that for example, in each layer we have 4 exports, and for different experiment, for different tasks, the different export can be activated in. So in that way, the inference cost can be reduced in such way. And the third part is the conditioning module. So consider the video condition. If we compare with the image condition, like the controllet or T2 adapter with the sketch, the depth information, or the key point as the control factors, controlling information, the video generation, I think it maybe need more conditions such as the optic flow maybe it's relatively unique to video control. So our current framework, we have updated some conditioning module in our framework, and you can also pull request to maybe develop more controlling factors for our video generation. And but we know that currently the text control is still the most important part, and also what we do is text to video generation, the T2V. So for such video text generation, maybe in the next version, we will train or promote. We will design or prompt refining to refine the user prompt to the expressive description, because we found that the user always don't know. Even for me, it's quite hard for me to write the correct or expressive prompt to generate the video. And currently, we use the T5 as the text encoder. And for this part, the most important thing is not the text encoder. Actually, it's the data preparing, because we need high quality video text data pair. So we need to do video caption based on the video training data. So as we need high quality training data, actually high quality video text data pairs, we have two solutions to do this, to do data prepare. The first solution is that we can get the high quality video data online, then use some good model, some great model, the video caption model, to do text annotation, such as the GPT-4V or Video Lava. But a big problem is that such model cannot always get our good results, correct results. For example, here is some African buffalo crossing a river, but you can see the model is annotated this video as the various peaks. So such wrong annotation cannot train a good generation model. So to overcome such problem, we also do some more work. We first of all, we use, because you know the GPT-4 vision is for the image annotation. So we can combine many video frames as one image and to do annotation. We also train, we also cooperate with the Shanghai AI Lab to develop a new video caption model. It's named as Shared GPT-4 Video. This video caption model has 4 capabilities. The first capability is that the sliding caption. The second one is the fast caption. The fast caption is similar like the an image grid, can be words or video. So but it's only need one inference, and it's need very lower cost than the sliding caption, and we can combine the keyframes and get our image grid and caption the video. The third capability is the clip summarization. And the most important capability of this model is the prompt recaptioning. So this capability can generate the Sora-like prompt. And our next version actually, because this model just released last week, and we are using this model to do video annotation, and our next version is training based on this text annotation and video data. So if you want to use this model, you can also just Google search. This is our research work, our paper, and also you can go to the GitHub to use this model. The second solution is that, because if we always use the video caption model, you cannot 100% to guarantee that your model can get your can give you the correct results. So our other solution is that we can do the text-driven physics engine to synthesize the video. So that in that way we can get the result with very high video text and alignment and fine grainedness. Also, we can also apply some knowledge of the physical world to the video. For example, here is some basketball falling down, and or t-shirt fluttered in the night window or strong wind. So this is use text to drive the physics engine to synthesize the video. So currently this work is actually in progress, and but now we can generate some video from the game, computer game. So here is an example. Under a clear sky on a control road, with bushes and grass huts beside it, a white-haired man carrying 2 swords walked for some time and then jumped in place twice. You can see this has a very high video text alignment by using the text to drive the physics engine or the computer game engine. So we are collecting such video text data for training our next version. And for the model training, we also need to, we also wish that because the Sora can be compatible with different video input resolution and input duration. And for our model, our research, our plan, we also want to do the much resolution and the much duration input training. So we also have 2 options. The first option is that use attention mask mechanism. As you can see, different image resolution, we can use the attention mask and get the to change it to the same ratio. But we have verified that such way is effective, and in our model. The other option is same as the technical report of Sora. That is the NAVIT, the LAVIT. The LAVIT module also has been integrated into our framework, but we don't have more GPU to verify the effects. So if you have more GPU, you can verify. Maybe you can verify it, and you can just after you verified it, you can email to us or just pull request in our GitHub. And the good news is that the Alibaba, one research group of Alibaba want to verify our current our LAVIT in our framework. So maybe next month we can get some results. Okay, the third part is our current progress. We have released 2 versions, the version 1.0 and 1.1. And this is a generation result of version 1.0. So in our first version, we can only generate 3 seconds, but in our current is we can generate around 10 seconds. But you can see the quality is not very good in the first version. And then is our current version. I really like this one. This prompt is come from the Sora technical report. There are many different television showing different programs. For Sora, you can see the detailed information in each television, but in our model, you can just, we don't know what's the detailed information in each television. And the other one, and the more, you have been see this before. This is an orange shot of a lighthouse standing on a rocky cliff. I like the camera changing actually. Besides, we can also generation, our model can also training and inference on the S and NPU, not only to GPU, because in mainland China sometimes we cannot get enough GPU, as you know the reason. So we are also trying to adapt our model to the NPU, and our model also can compatible with the text to image generation. Here are some examples of the T2I results. And then the next part is our future plan. So first of all, let's look at the example of the scaling law by the technical report of the Sora. So here is the Sora, the best computing. If they apply the best computing, the result is like this. And after 4 times computing, you can see the quality is improved very significant. And after 32 times computing, so you can see, as you said, the Sora claimed that, the OpenAI claimed that the diffusion transformer are scale effective as a video model, as a computing. So how about the same prompt to our model? Our current model, you can see, is a little bit weird. The head showing. But we believe that our result is similar as the base computing. So our next step, we will trying to just use more computing cost and scaling up our model size. Our current model size is only 1B. Maybe in the next, we are training the 3B model in our next version. And our plan has 3 stages. The first stage is we already is aim to verify our framework, and this has been finished. Currently, we are in the stage 2. In the stage 2, we want to use more data and a large model to train a model which can generate the video with 720p quality, and the length is larger than 20 seconds. Also, this is our final goal of this open source project. The computing, we guess the computing request is 1000 A series GPU or 500H GPU. The good news is that we have get 500 NPU, the asset NPU, and also our company has provided more than 100 H GPU for us for this project. And the data maybe is larger than 200 T, but now we already have 300 video, high quality video. In this 3D3 is not our final goal, because I think for open source, because this, I think this is just similar like the Lava 1. If we can reach this goal, I think we already achieved the open source plan is very success. Besides, as I mentioned, we can train our model on NPU. So we did some native code development on the NPU. I also do the speed up by mix the precision and the flash attention on the NPU. And also we found that the deep speed can also extend to the training on the NPU. So we also developed the long sequence for long video. After the optimization, the NPU can reach the A100 in our framework. The training efficiency, you can see, is quite good actually currently after the optimization. And also we do the deep speed and the transformers based on the NPU equal resource. Here is some needs, some adaptation we do. We need to do some adapted operations on the NPU. It's a little bit different as GPU, you can see. Here is some codes. And also we have released our, last month we released our current version. Next month we may release our next version. And also because this is open source plan, and we wish that the community can collaborate to do this plan. And we also list the to-do list, give a very detailed to-do list. And you can see some task has been done by different people. So we hope that all the community can maybe contribute to this work, because we claim that because we will also release the model and as a open source project. So that's all. Thank you.
Thanks for Professor Li Yuan to introduce the brilliant work, Open Sora. We know that Open Sora is one of the most popular projects in GitHub, which can load long video using compression technologies and also using MOE to accelerate the inference speed. So do we have any questions? I think we have one online questions and you can you see the online question?
I see.
I think you are already answering that.
Actually, we use the MPU of the Ascend 910B. In the maybe in the future we can use the 910C, the Ascend MPU. But we use both GPU and MPU for different parts, different model size training.
Okay, I have a here.
Yeah, I'm wondering about the video recognizer. Is VAE or VQVE?
In our first version, we use VQVE. But in our current and in the future version, we use VAE. It's actually, we found that it has less, it's both okay to use the VQVE or VAE. This reconstruction result is based on the VAE, you see. And actually, this one is based on the VQVE. But it doesn't matter.
I think we have another online questions.
Okay, how many GPU we use in DIT in total? Yeah, in our current version, we only use the 64 H100 GPU to training the DIT. But in the next version, we would like to use more than 200 DIT, thanks to the company to provide this GPU for this project.
Any questions? Okay. For the 3D vision, so for encoding for the very long video, that couple that what use of the memory, and the video is very long for the after minute, so it's happened from frames. So if that we encode that both together, then that the memory for how to solve that, that happens.
Sorry, I cannot hear the question. It's not very clear.
Can you sit closer? Yeah, I think you can sit on the first floor and repeat your question. Yeah, so Professor, so my question is that for the very long video encoding and decoding, I mean, use a 3D VAE. So is it possible that the out of memory, I mean that they have the over 1 minute video will be over 100 or 1,000 frames. So how to solve the problem to keep the memory efficient?
Okay, that's a good question because we use 3D VAE to compress the video. You see 1,000 frames. And currently, we cannot. We can only compress the one. You can see 1 minute video. So sorry. There are some methods to improve the GPU memory. I mean, you can see in our current version, we changed the 3D block, 2 3D blocks to 2D blocks. But we still need the 3D block to compress the temporary dimension. So this we can also this cannot only be more capable to the image and the video reconstruction, but also can reduce the GPU memory. But that is just one trick to improve the memory efficiency. There are also we believe that we still need to improve the maybe more powerful 3D VAE, which can achieve higher compression. So maybe 500, more than 500 compression ratio. So the other way is that so we believe that in the next version we will show some more better results.
Any questions? Yeah, you can see, you can maybe more closer.
Yeah. Sorry. So my question is about this usage of MPU. I haven't really seen a lot of people using that before. I kind of wonder, so how good is your compared to GPU in your experience developing this open Sora project, and like does it support like really large scale training, or do you have some specific obstacles in mind you think that's noteworthy, like during the either the training phase or the inference phase of the Sora model? Yeah, thank you.
Maybe I cannot hear all the question. It's not very clear. But I think your question is that how to guarantee the large scaling training. Is that your question?
That's the question.
Okay. So as as I mentioned, it's not easy actually to do large scale training because we also have less experiments before because we cannot always get such more like 1,000 or 500 GPU or NPU. So we actually, if you go to our open Sora plan, the repo, the GitHub repo, you will see we have different branch. Some branch, may, like the HW branch, can support the line, the ASIC, the NPU training, and this efficiency has been optimized by our team with another NPU team. So basically, we need some supporting from the HPC people. The research, some teams from here, they're supporting to do the large scale training. So what we are focused on the model, the algorithm, verification and the designing. So for A100, it's not it's easier actually because the ecosystem is quite rich to do the large scale training.
Yeah, I think if you have more questions, you can contact Li Yuan. For more, you can. I will leave the context information of Li Yuan, and you can contact email him for more details. And thanks again for Li Yuan's brilliant talk.
Okay, thanks all.
Yeah.
Bye.
So let's move to the next session. So.
All right. So let me introduce Hao. Hao is an associate professor of computer science at the University of California, San Diego. He's the director of Embodied AI Lab at UCSD, also a founding member of the Data Science Institute. He, mainly works on algorithms to model, understand, interact with the physical world. His, interest span computer vision, machine learning, robotics, and embodiment. He obtained his PhD in computer science from Stanford, and he has been since serving as area chair and associate editor for nearly all the top computer vision, computer graphics, robotics, and machine learning conferences. His, PhD thesis received the honorable thesis mention award and also the NSF Career Award. So very happy to have you here, Hao, and over to you.
Okay, thank you so much for the introduction. I'm very honored to be invited and give the presentation here. I think maybe in Zoom I didn't enable the voice. Oh, it's on. Okay, great. Sorry. Okay. Yes, so I work on a broad set of problems, both on the 3D understanding and on the robotics. For this workshop of foundation model. Oh, I'm sorry. Which is screen one? Oh, only one. Okay, thank you for your patience. Right, so for today, I'm going to focus on the foundation model of the 3D vision because this is CVPR. So the topic will be like generating and understanding the 3D objects in an open world. Well, I started work in the field of applying deep learning to 3D data pretty early at the very beginning of this field. At the beginning of this field, people work a lot based on a very small number of object categories. Like we work on human body, we work on chairs, and perhaps a very small data set of objects. Like I remember there was a benchmark for 3D retrieval, which only contains 90 instances. Well, we introduced a data set called the ShapeNet in 2014 that enlarges the number of object categories that people can play with to the level of a few tens of thousands. Well, we actually have a few million, but we were not able to release it, right, because of some of IP issues. But recently, the field makes progress and are witnessing larger data sets like Objectverse, which is really starting to, people start to have like a million scale of 3D data to play with. So that makes it possible to think of how do we push the research from only like chairs or human bodies to more open world. Okay, for today, I think, I have kind of plenty of time. I'm going to cover two topics. One is to build the open world ability for 3D generation, and the other is to build ability for 3D understanding. So, well, here I'm emphasizing the open world ability, but well, the workshop is named as a foundation model, right? So I would think like these two are strongly connected. And open world ability is a necessary step towards multi-purpose foundation model. I'm also going to show you how, to what extent are the 3D models foundational. Okay, so let's start from the 3D generative models. Well, the past decade has made great progress for the field of 3D generation. I'm going to use one of the pioneer work from my group, 2017, as an example. You'll see like we were working on single image-based point cloud reconstruction, actually generation at the time. And given the interesting fluffy pig, it's able to generate this kind of very loose set of point clouds. But we can do much better now. Look at the bottom side, and this is our latest work, that from single image, we're able to get high quality geometry with high quality textures. Okay, so let's revisit a little bit of well, what has changed and make this kind of a transformation to take place. Well, take the 2017 work as an example. That work actually already was using the variational autoencoder, but we were not using diffusion model at the time because it was not even invented and get popularized in the field of machine learning. Okay, and then for the representation at the time, we were using point cloud, and you see like we were not really using like the neural representation or the extended version of point cloud as a Gaussian splatting. At the time, we were also using the geometric loss. At the time, we were actually compare the Earth-Moore distance or chamfer distance between the prediction and the ground truth. Well, there were not explicit like a rendering loss used, so the visual quality are not so good. Now, in terms of data at the time, that model was already trained. I mean, like the one that works for the pig was already trained on 200K shape-net data. So in terms of change of data, in fact, you see, we increased, but not so much. So the amount of 3D data on the internet are kind of limited. And therefore, to achieve open world ability, we have to think of smarter ideas. So the work has two kind of limitations. One is like the quality, geometric quality details of visual quality. And the other is the generalizability. Well, the issue of representation or quality were first addressed. This is largely by the invention of using rendering loss. The nerve, Gaussian splatting, they are all works that use differential rendering, either volumetric or rasterization, or even like the studies into differential ray tracing, right? And for our work, a missed nerve that tries to leverage the nerve representation in a generative setup, which is a feed-forward network that gives 3 images from sparse views to predict the volumetric nerve. And this one was already using the rendering loss, and it is therefore able to achieve very detailed results. But open worldness is still quite a challenge. Now, the promise to solve the open world ability for 3D AIGC only took place very, like 2 years ago. Basically after like the 2D foundation models such as Stable Diffusion were invented. And then since then, people think of like clever ways to stimulate the internal ability of 3D for like 2D foundation models, or to use them as the discriminator to optimize the generation of 3D shapes. Okay, so earliest open world 3D generative models basically will say for the 3D model at the different views, after you render it, they must look realistic, which is a kind of a render loss based approach. But they're actually time consuming and memory intensive, and also they actually lack the guarantee of the global good property. Like you often see a model is able to generate 6 legs for an animal or 2 faces for a human. So there are also the introduction of the feed-forward kind of 3D generative models. Like there are basically 2 steps. The very first step is you're going to use some 3D data to fine-tune the 2D foundation models to achieve multi-view generation. And then the second step is like you're going to use certain kind of 3D operators or 3D native representations to convert the multi-view images into a neural representation. Our work at 1, 2, 3, 45 is like this kind of a category. It actually fine-tunes the 0, 1, 2, 3, the stable diffusion to have multi-view images, and then apply the MVS nerve kind of idea to convert the multi-view images to become a 3D model. For this pipeline, it doesn't have the genus problem because it's trained more globally for novel view synthesis. However, the limitations, one is for this approach, you are predicting multi-views and you're going to take the multi-view as the input to generate the 3D prediction. And then the consistency of multi-view prediction is actually always a bottleneck of the final performance. And then the other kind of challenge comes from how do you design the 3D priors or like the 3D operators to give you high quality geometric results. So the follow-up work 1, 2, 3, 45 plus plus tries to address those kind of challenges. We first try to think of generate more view consistent, more consistent multi-view prediction. Well, for the previous work, when we follow the idea of 0, 1, 2, 3 to generate multi-view images, it's like a single image. We give the viewpoint to generate and get one. And then if we have a lot of views to generate, then we generate the views one by one. But we also try to have an improved version that will generate the multi-views simultaneously. And then along with the generation process, there are the transformers to allow the different views to talk to each other frequently. And therefore, you'll be able to get a much more consistent multi-view generation. This is the 0, 1, 2, 3 plus plus work. And we have been upgrading this, and we have open sourced it, and so that everyone can use it. And this actually is a very popular work used in a lot of recent 3D generation feed-forward pipelines. Okay, so then if you have like multi-view images, and you are going to lift them. Is it working?
A few seconds now.
Okay, you're going to lift them into the 3D space. And we actually take a two-stage approach. First, we generate a coarse 3D volumetric representation, and then we refine it. Okay. Refine it to get a higher resolution. And you can take a look at the results that are given a single image. This already start to give you high quality geometry and high quality material, well, relatively. Okay, so I would want to say that I'm actually basically illustrating the progress of the field using the representative work from my group, but there are the concurrent efforts for improving the multi-view prediction and also the sparse view reconstruction. Well, so after the 1, 2, 3, 4, 1, 2, 3, 45 plus plus work, there are also some other improvements that we have done. And here I will pick two exemplar work. One is the mesh arm work, which we collaborated with Adobe Research. So this work assumes very sparse view as input. But if you can use 0, 1, 2, 3 plus plus lift as a single view to become multi-view, you can fit its input. Okay, so here the basic idea is to petrify the input image and put them in a big pool and use transformers to generate the tri-plane representation of the radiance field. And then this passes through a differentiable Martian cube pipeline to be able to extract the mesh. And the 3D texture is also generated in the feed-forward path. So you can see like this is fully transformer-based architecture and is actually giving a good robustness. I would say like the open worldness still comes from the 0, 1, 2, 3 plus plus for lifting a single view to multi-view, but is trained with the object-verse dataset, which actually learns the local geometry priors to be able to generate sharp results. So to put it simple, if you think like this is kind of a 3D foundation model, then here the open world ability still comes from the 2D, and then the 3D geometric prior locally are from the 3D. Okay, so there are certain tricks for training this pipeline effectively. The core trick is like, well, we actually can have an end-to-end pipeline very well trained using the rendering loss. Here, because the final outcome is the surface, it's the mesh. You could think of using a differentiable rasterization or like some kind of a differential surface rendering loss to train it. But you will see like you will get stuck into a lot of local minimums because surface optimization involves like the change of topology and deformation, which is very tricky. So practically, we find it's more effective to have a two-stage training. The first stage is to consider like effective training for volume rendering loss. The volume rendering loss is like it's kind of like you're optimizing, think it as optimizing like the occupancy for every cell. And think it this way. And then largely, this is relaxed the problem of the surface rendering. And because the variable space is larger, it's a lot better in terms of avoiding local minimums. So the two-stage training is like first apply the volume rendering, which is a relaxed optimization problem to solve and get the initial point, and then refine it with surface rendering to convert to a better local minimum. So that's kind of idea. And I'll show you some results, like we can start from text and use some kind of, like for example, some kind of text-based generation approach to give like single view or multi-view images. And then from the sparse view input, run the pipeline to generate high quality mesh. Okay, and you can do this also from single view as image. Somehow for that previous pipeline, it's an entirely transformer-based idea. And well, what is a little bit unsatisfying to me is like there are not really some 3D native priors applied. As we're predicting triplane-based representation, which is very much 2D. So entirely, it's like 2D, right? The petrified. And other than the part, the triplane is actually a compressed 3D representation. So we think of some ideas. Are we able to still leverage the 3D native priors, like 3D proximity? Will encourage people to think of 3D convolution or up convolution. So for the other approach that we recently pushed out, which is called the mesh former, that's a combination of the transformer idea and then the 3D native convolution up convolution operator. Now to put it simple, you can think it less like we are still using the cost volume or 3D convolution kind of idea for certain processing, but we compress the feature into a low dimension space, like 1D space. And there you can easily do transformer to do a lot of global information exchange. And then you somehow still use like the 3D native operator, like up convolution to get or sparse convolution to get the detailed geometry. We find out that this version will give you actually even better local geometry, and that can give very sharp results. Okay, so we can also extend those kind of well, maybe you can also call it 3D foundation model, because they can support a lot of applications. Not only can they do like text, but also they can do the multi-view based capture. Like for example, leveraging the 3D priors. Now for you can easily pick a video, capture a video of a certain object. This is a pretty arbitrary trajectory without a strong requirement, and then get the geometry with good texture. Well, the entire process gets very robust. Can become an off-the-shelf tool. So that's a process, and you can get an understanding like as an entirety, the 3D generation is starting to reach a level that can be called a foundation model because it supports open worldness and because that is easily supporting, providing a very strong basis for providing for solving a lot of different kind of problems. So what's next for improving this? Well, the very number one problem everyone might be interested is like, or it's actually the shared issue of all the foundation models, which is what is the objective metric, right? So nowadays, because we're using more and more data for training, even for the evaluation data, they get contaminated, and also, there are a lot of commercial behaviors, right? So everyone is like advertising their own work. At a generative model, finding a few working cases, that's easy, but guaranteeing the robustness, that's tricky. Okay. So for the pipeline, we think like the bottleneck is still like, if you are taking the fine tuning of the 2D foundation model, then you still have to guarantee the consistent multi-view representation. But any kind of a inconsistency may have certain consequences. Although you have the 3D prior to rescue the pipeline quite a lot, but you still are in a risky position. Okay, are we able to significantly improve the consistency for the multi-view prediction, or are we able to significantly improve the robustness of the view lifting so that inconsistency can be addressed, or actually should we consider to pursue multi-view free? But if you do the multimodal free, how are you able to still borrow the force from 2D foundation model? Okay, these are very deep research questions that we're further thinking. Okay, so there are some other kind of questions interesting, and I want to particularly mention one, which is the part level generation. For now, although I'm showing you a lot of fancy and interesting results, right? They actually are just a generation of an object shell. Well, the models to be used in the digital twin setup or in the metaverse setup, they need to be interacted in a functionally proper way. And a lot of times this is requiring like to having the proper mobility part. And if you hand your 3D generation to artists to edit, to do post-processing, a lot of times they also require like there are certain like structure assumption, so that when they edit one region, other regions get less affected, and there are topological requirements. So there are actually challenges. Okay, so that's the part for introducing the progress for building the 3D foundation model, the foundation model for 3D generation. And then the other part is like the foundation model for 3D understanding. Well, somehow this I'd still prefer to separate the foundation model challenge for the 3D into the two big categories, because I feel using a single model to unify them is probably not quite possible. Okay. I'm going to introduce some of the efforts that we made towards pushing the 3D understanding foundation model. Largely, you can think like the 3D generation foundation model is to push the 3D version of DALL-E. But for the understanding foundation model, we're asking, are we able to push the 3D version of a clip and a 3D version of, like, for example, maybe GPT-4V? Think of this way. Okay, so right. So let's first look at our previous efforts of pushing the 3D foundation model, which is kind of like the clip flavor, which can be thought as a strong pre-training approach, and to build a joint embedding space for images, text, and here the 3D geometry. Okay, so for the field, we're pushing building a joint representation for images and shapes. This also is an effort for quite a few years. Like my 2016 work, publishing SIGGRAPH, is probably one of the earliest work for using deep learning to build a joint space of images and 3D models. But we were not able to anticipate that the progress in the text understanding is so fast that today we can also talk about like in building the foundation model, or not, I don't use the word foundation model, which is joint embedding of the three modalities. Okay, so as similar as the construction of all other kind of large models, the most challenging part is to get the data, especially annotated data. So for us, with the help of the Objectverse, which is kind of a large data set, we were able to tag them. And especially you can think of like render 3D shapes into images and automatically tag them to become text. And then you can use a way as similar as clip to train a joint embedding. And this, well, could give you some very interesting results. For example, you can talk about like the geometric interpretation between a banana and a ship to get those kind of banana-shaped objects. Okay, and this also allows you to like use text to retrieve 3D models, or even to use point cloud, the other point cloud, the first column. They actually look very dense, but they're actually sparse point clouds to retrieve 3D objects similar to them. This is kind of a retrieval effort. Okay, another part, group of work I want to put a bit of time to explain is to build the kind of like segmentation foundation model, which is, you think, like the maybe like the SAM or like grounding dino, right? Like GPT-4V. So we start to explore the problem from the work, from the 3D part segmentation. But I'm going to show you, like in the end, we also get a pipeline that can do scene level segmentation. Okay, so one of the reasons for us to be particularly interested in part level segmentation is because you probably know, like I also work a lot on robotics. And I think of my 3D understanding, 3D synthesis may benefit our push of robotics, which is, you know, the very ultimate form of intelligence, the intelligence with the body, embodied AI. So somehow when robots or human, we interact with objects, actually the most of the time we are interacting with parts of objects, right? Like when you're talking about opening the door, opening a door, right? This is about recognizing the handle and then approaching your hand to the handle and grasp it. And then once you're able to do this kind of a door opening, you're able to open like the door of a cabinet. You may like a microwave, right? I mean, even dishwasher, different orientation, right? Or washing machine. So that's kind of like a part allows the generalizability for skills. So we are anyway pretty interested in understanding the parts. To be able to build robots that can freely work in the natural space in an open world manner, it actually has to recognize the paths of arbitrary objects, which is the open world path understanding. How can we achieve that? Only with 3D data, we're not quite able to achieve the goal, at least 2 years ago. So we take a two-step approach. That first we have the 3D models to render them into images. And then we can apply the 2D foundation model and then transfer the knowledge back to 3D. This is kind of like a view-based aggregation. So if you do this, this is our work at Partislip, and also there's a follow-up work with Partislip++. And we have a part-level segmentation model that can do zero-shot, a very few-shot learning for point clouds with high quality. But the drawback of the pipeline is like, this is not really 3D native, and you have to run a 2D foundation model sometimes, you know, when the point cloud is really sparse, it's problematic. What we have discovered is like, if your point cloud is very dense, you can render it to become a point cloud image, and models such as SAM or GPT-4V do not really have strong domain gap to recognize it. But if the point cloud really gets sparse, the domain gap is still there. Whereas in our 3D space, we have a lot of networks, especially like a point.net, have demonstrated, even for very sparse point clouds, is able to process the semantic understanding well. So what I mean is like, if you really have sparse point clouds, probably rendering them into images and then use 2D foundation model to analyze it is not really a good way. You still have to think of a 3D native foundation model. So which is our very recent work of pushing like the SAM for point cloud, we call it the point SAM. And this is the 3D native SAM, like given a point cloud, you partition it into a lot of small groups, and then use point.net to process local groups so that you get a pretty robust feature regarding like the sparsity. And then you apply the VIT kind of idea using transformer aggregate information, and then do similar kind of pipeline as SAM, right? You use parameter points to predict local masks. So let me show you a little bit of results of the point SAM that you can actually, this is the left is a point cloud of an unknown scene, and you can put a single point, and it does a SAM like a proposal generation, and you can also put like a negative prompts so that only the object of interest is labeled. I'm sorry that is a bit small. It's a top view of a room. And then for the right, I think it's an even better example to show the open worldness, which is like some monster that the model has never seen in the training time. So you can still see like it's able to segment the part of interest out based upon the prompt. Okay. Okay, so I've introduced some progress on building the foundation, well, achieving the foundation model ability or open world ability for 3D generation, 3D understanding, and to give a conclusion that the ability for open world in a 3D space is emerging pretty fast, especially for last year. I think just a lot of breakthroughs. And the fundamental idea is still like 3D can be connected with images easily. and then you can transfer another knowledge from the image space to the text, to the 3D space. Somehow I can also see a kind of trend that, you know, even for the training of stable diffusion, right, you are using the pre-training by the language data. So the knowledge is to some extent is transferring from the language side to the image side and then to the 3D side. But this 3D side hopefully will bridge the gap between the agent and the physical body, and then in the future will allow us to extract more data, more knowledge from the physical world and transfer back from the 3D to the image space, maybe to the text space, or directly from 3D space to the text space. Okay, so we see like we think of clever ways to leverage the 2D foundation models to solve the 3D problems. And we need to incorporate the 3D native priors, which can help us to get 3D consistent high quality results. Okay, so that's it for my presentation.
Thank you, Hao. Any questions?
Yes. What do you think about vision model, which could have like Sora, for example, which could have a 3D aspect?
That's a good question. I'm both positive and negative about Sora and the 3D ability. For the, right. First of all, I think like video actually has a lot of 3D knowledge, right? And Sora is kind of like the way of extracting the structured knowledge out of a video. But in terms of 3D, I'm always a little bit skeptical about like whether we can really use Sora to achieve like long video modeling in a holistic manner without incorporating explicit 3D priors. I think my words are well, sentence is a little bit complex. For example, like doing a slam, right? You go drive in a city, or the robot roll on the floor, and then form a closed cycle. And to what extent can Sora give you a cycle consistency? I guess for small, short trajectory, it is able to some extent. Some people have tested, not quite perfect, but it can support a nerve to do a little bit of a reconstruction, not at high quality. Yeah, which means like it captures some 3D spatial information, but not at high quality. What about if I will have a longer trajectory? Like for example, think about a car driving in a city, drive it for, I don't know, maybe 10 minutes. Without a 3D native map at the back to support Sora, I would not really anticipate that it's able to give you the loop closure. Yeah, so somehow I think like putting the 3D thought and the video generation thought together, this can be a very interesting direction. Yeah.
Thanks for the great talk. I just want to ask, do you think there will be scaling law in 3D?
Scaling law in 3D.
Like we can say model like reconstruction model on algebras, or faster on like what data we have now. So using
I want to think about the two aspects. First of all, RM is a multi-view input problem. So that's a sparse view problem. And what it needs to complement is actually like, it's largely kind of an interpolation problem. Yeah, so that's not really quite a generative model. And under this kind of a setup, the object-verse level of a data set is roughly sufficient. Okay, so but if you're talking about single view to 3D reconstruction, that's a very different kind of problem. For an object that is not really covered by the object-verse, how are you able to predict what it will look like from other views? It won't. And you still have to think of other approaches like using 0, 1 to 3 plus to predict other views. Yeah, that's the point that object-verse alone, I think, will not be sufficient to give you such kind of generative model. I would say yes and no. I wouldn't say it's trained on object-verse. I would say it's fine-tuned. And here, the point of fine-tune is to stimulate the internal ability of Stable Diffusion for understanding the other views. It's only stimulate. So how you probably won't even need the size of the verse to stimulate this ability. This is the one side. The other side is if there are certain kind of a very soft objects, highly deformable, Stable Diffusion does not capture the power strong enough. So this stimulation will also not work. Yeah. Yeah, so I would think the combination of using the 3D data reasonable amount just to stimulate the internal ability of Stable Diffusion, and then for open worldness. And then the other part is to use the regular geometry captured by, like, for example, or reversed to achieve regular structure in terms of 3D reconstruction. We are cleverly combining the two abilities together to achieve a good final result. Yeah, I would not say object-verse is large enough for open worldness, for accounting for the open worldness of like single view-based 3D generation.
We have one more question.
First, great comment. And I have a question. So the 3D object generation has been like getting amazing results over the past few years, right? But as far as I know, I haven't seen a lot of like 3D scene generation, right? What kind of like the major bottleneck on top of your mind?
Yeah, that's a great question. I think the question can come from various aspects. Object understanding does require a bit less data because there are stronger symmetries, regularities. So when we do not have a lot of 3D data, starting from object level to kick off the open worldness research, I feel like it's reasonable. The field moves step by step from object to scene. This is natural. This is reason one. A second reason is like what is the proper or good representation for scene? That's quite an issue because for object, in the end, the triplane or volumetric are reasonable. Basically memorized, we can forward it. But for scenes, you definitely need sparse representation. And whether you will sparsify it by hashing, by sparse voxels, by view depths, there are a lot of uncertainty. It's a lot more immature in terms of representation. And if you talk about data, it's even true. And I would even say I'm not so clear whether we are going to pursue a scene level generation model as in the image space, because it's also possible like we're going to have object to arrange and become a scene. Like maybe we only need a coarse scene model to provide the basic layout estimation and then replace the objects by the very detailed objects that we generated. So if you consider that, what is the goal? What is the quality expectation for scene generation, given the practice that we don't have too much data? Yeah.
Any more questions? Maybe I can ask one question. So, for example, for OpenShape, these are all synthetic scenes. How do you see, like, can the same pipeline generalize to real-world objects, like real-world data? What's the gap between synthetic and real-world data?
Okay, great question. First of all, the sim to real gap might be different from what people have thought. You might think like the appearance are different. This is the creating a domain gap. But from what we observe is this appearance difference do not create a domain gap almost. Like I mentioned, even if you are rendering a dense point cloud to become an image, GPT-4V, SAM can do it pretty well. The real gap comes from occlusion. Because when we were training open shape, we are basically training with complete objects. But in reality, objects are occluded in ways that are reasonable. Okay, so the primary obstacle comes from addressing the occlusion challenge. Yeah. Anyway, I would think of making an example. I mean, when I'm working on robotics, I'm always annoyed by the questions about symmetrical domain gap in the visual domain. I would say like that's because the model are weak. Like for humans, we do not have this domain gap. If we are believing like foundation model are getting stronger, approaching human level, then you would also believe the domain gap issue is also annoying the foundation models less and less. Yeah, so that's kind of my understanding. Yeah.
Thank you.
Mm-hmm.
Yes.
Hi. In the talk, you talked about two kind of models, one generative model and another discriminative model for 3D understanding. I kind of wonder, like, can you like use them together? Like, first use some generative models to generate a bunch of data, and then train the model on the synthetic. Maybe together with the real data, technical real world, like a more broadly known.
Yeah.
Like 3D models.
Yeah. I completely agree with this kind of idea. I think as we mentioned, in fact, there is a data flywheel that is hidden in my presentation, that we are transferring knowledge from text to image space through stable diffusion. Like stable diffusion, there is a pre-training by text foundation model. And then the further propagation of knowledge from image to 3D space, right? And this would allow us to have a larger synthetic training data, which allow us to train a better discriminator, or like the understanding model. That I completely agree. Yeah.
I think this problem is this question is more or less related to the previous, like, okay, because the model is also like trained on a 3D data set. Would you agree that the generative model actually mirrors the image from another?
Yeah, well, I want to emphasize again, like from at least by my view, the model like zero with the help of 0, 1, 2, 3 plus plus, like the model as like 1, 2, 3, 4, 5 or mesh RM, they are a lot more powerful and they generate a lot better than observers. My understanding is they are capturing a distribution much wider than observers. The key is not observers. The key is like to fine-tune stable diffusion to transfer knowledge from other domains. Yeah.
Thank you.
Mm-hmm. That's my understanding. I might be wrong. Yeah.
Any further questions? Okay, so if there are no further questions, let's thank the speaker again.
Oh, by the way, I just want to add one more sentence, which is like, I know there is a very recent work from, I guess, the group of next speaker that, I don't know, are you speaking next? No. Oh, sorry. I mean, I heard like there are people like there's one recent work I want to advertise for them a bit. RM 0, which is like they use synthetic data to train the RM, which works almost as well as observers. So yeah, you see that, right? Yeah. Mm-hmm.
Yes.
Am
sure.
I
have
using too much time? Mm-hmm.
I saw like lots of open works that's really static objects. So what's the idea of how we can explain that? Because if we take pictures, I'm thinking like there's not only lots of stuff like dynamic. We want to use the foundation model. What's the parts for dynamic objects? You have an idea how we can like.
I think like I understand like there are just many people who are interested in building a 3D version of Sora. When they make this kind of claim, they are almost trying to solve the problem you were just defined, right? To be able to generate 3D dynamic objects or scenes.
Maybe we can continue the discussion. Right, so with this we come to